distinguished paper.
Yes. Thank you for the introduction. So thank you also everyone for coming. Today we're going to talk about NDEF, why we no longer want it in LLVM, and how we can remove it. So to give you some context, currently Alive2 finds about 136 miscompilations in the LLVM test suite. 25 of these tests will become correct the moment NDEF would vanish from LLVM, which is about 18% of the total failing tests. Notice that these tests are only unsound because NDEF exists, even though the majority of the tests do not touch NDEF explicitly. Throughout the years, the LLVM community has managed to remove about 58% of total NDEF users, but currently progress has plateaued as the remaining, almost all the remaining users of NDEF are concentrated in loads of uninitialized memory. So what actually is NDEF? So as many optimizing compilers, LLVM has two kinds of undefined behavior. The first kind is immediate undefined behavior, which is reserved for operations that trap the CPU. Deferred undefined behavior covers all the remaining cases. So LLVM has three main forms or values to represent deferred UB. So the first form is poison, as you can see there, which is sticky and propagates like floating point NANDs. The second form is NDEF, which is mostly used nowadays to model loads of uninitialized memory. Notice that every time we read an NDEF value, we may get a new different value. Freezing a poison or NDEF value gives us a non-deterministic but fixed arbitrary value through the freeze instruction. Then, at the bottom of the lattice, we have regular values. Notice that from these values, only poison is sticky, while NDEF is not. This non-stickiness of NDEF gives it some counterintuitive properties. So, for instance, consider here this optimization where we want to transform 2 times y into y plus y. So many of you here might think that this is clearly a valid optimization. However, it is actually not, only because NDEF exists. To see why, remember that every time we read an NDEF value, we may get a new different concrete value. This means that in the program on the left, we have a single, if we consider y to be NDEF, we have a single NDEF read. So we get an arbitrary value, we multiply it by 2, so we get an even number. However, in the right side, we have 2 NDEF reads, which means that we read NDEF twice. The first read could be, for instance, 2, and the second read 1, which gives us 3, which is an odd number. So we went from a program which gave us only even numbers to a program which gives us both even and odd numbers. So the refinement is clearly not valid. So if NDEF can cause these subtle bugs and get in the way of optimizations, why is it still here? As I mentioned already, the remaining uses of NDEF are almost all come from uninitialized memory. We want to change uninitialized memory to poison. However, we first must address 2 main blockers. The first blocker are bit fields. So Clang currently uses a read mask write pattern to write and mask bit fields. And if we change uninitialized memory to poison because of poison stickiness, this pattern breaks. The second problem are raw memory copies, which are currently unsound in LLVM. Changing uninitialized memory to poison would further aggravate this problem, as we would get more poison values in memory. So that's not something that we want. So let's now explore each of these problems in more detail. So the first blocker are bit fields. So to store bit fields, Clang reads the whole word, masks it, and then writes it back to memory. So in this example, we have these bit fields, and to write to bit field A, we load the 32 bits, then we clear A's bits, and then we store the value back to memory. Today, This is correct because undef is not sticky. So, because poison is sticky, if the original load contains a single poison bit, a single uninitialized bit, the whole load will be 32 bits of poison. Then we end up storing this poison value to memory, which overrides the existing bit field values. The second problem are raw memory copies. So LLVM currently lowers small mem copies to integer load store pairs, as you can see here. This has two main problems with using integers. So the first problem is that pointers in LLVM are not mere addresses, but also carry something that is called provenance. So provenance can be thought as the capability to access a memory region. So the problem with using integers is that integers do not capture this provenance. So if we load a pointer through an integer type, we end up discarding this provenance. The second problem is that poison is value-wise in integers, which means that if a single bit in memory is poison, the whole loaded value will be poison. This conflicts with memcopy, as we want to copy memory as it is without spreading poison bits. So switching an initialized memory to poison would increase the quantity of poison bytes in memory, which would make the raw memory copy problem even worse. So both these blockers boil down to the same problem, which is that LLVM cannot represent raw memory in SSA registers. So that's precisely our first contribution, which is a new byte type that can represent raw memory bits in SSA registers. Additionally, the byte type tracks poison per bit, which means that a single poison bit does not taint the loaded value. So previously, memcopy intrinsics were lowered to integer load store pairs, as you can see on the left. And now with the byte type, we preserve individual poison bits and pointer provenance. We also added a new bytecast instruction, which allows us to convert byte values to other types, perhaps integers and pointers. So the bytecast instruction comes in two variants. The type punning variant forces reinterpretation of the bits, and the exact version on the right returns poison if the type of the value encapsulated by the byte does not match the cast destination type. So for instance, consider that B8 value represents a single pointer byte. If we try to cast that pointer byte to an integer, we get poison back. So the byte type gives us more than just a sound memcopy lowering. Consider, for instance, this char type in C, which acts as a universal type holder. So it can hold the raw bytes of any given object in C. Also, char pointers can alias with anything, which is what allows us to write a memcopy implementation. So on the left, we see that we copy a single byte as we would inside a manual memcopy implementation. Currently, char lowers LLVM lowers the char variable, the char type, to integers, which is unsound because of provenance and spreading of poison bits. And with the byte type, we can preserve the raw bytes without coercing them and casting them to integers. Another application of the byte type is to fix existing optimizations. Consider, for instance, load widening, where we merge two consecutive loads into a single one. So the original code loads two values from consecutive memory locations. In the middle, we show the emitted IR by LLVM nowadays, which widens the load and then uses bitwise operations to extract the two load results. Combining the load is unsound because of poison. So if either of the original loads contain a single poison bit, for instance, if load 1 contains a poison bit and load 2 doesn't, the widened load will be 16 bits of poison. So in the optimized program, the first load and the second load will be poison. while in the first program, we get the first load with a valid value. So this is not a valid refinement. With a byte type, we can just load the raw memory because poison is tracked per bit, and then use the bitwise operations and the bytecast instruction to extract the relevant parts. Our second contribution is a freezing load to address the bit field issue, which is equivalent to loading raw memory, then freezing it per bit, and then casting the results to an integer. So this is what bit fields need. Clang currently has 2 encodings for bit fields. It has a fine-grained encoding, which aims to reduce the bit width of loads, and default encoding, which loads at the word level. So these 2 encodings should stay ABI compatible, and if we freeze the loaded value per bit, we avoid this poison spread. So when we write back to memory, we don't overwrite other possible existing fields. So yeah, with the freezing load, these 2 encodings stay ABI compatible. So we ran a live 2 over the LLVM test suite with our new 2 contributions and found that 11 of the previously flagged tests were fixed, which is about 8% of those I mentioned at the beginning, and we had no new failures. These tests include unsound memcopy lowings and unsound pointer coercions. We also verified the compilation of real C programs with the live CC, and we found that in Draco, 330 memcopy lowerings were fixed, 1 for eSpeak, and in all the benchmarks we analyzed, no new issues were reported. We also evaluated our benchmark across 20 applications from the Phoronix test suite, as you can see here. So here you can see 2 plots. On the left, we have the runtime performance, and on the right, the compile time performance. So notice that negative values here are better, and the average value is indicated by the dashed line. So with our new optimizations implemented on top of the byte type, the worst slowdown we have in runtime is around 4% in Cindy Johnson, and the average is about 0.8%. Compile time stays relatively unchanged with an average regression of 0.2%. So we analyzed the emitted bytecasts in our code and found that most of the bytecasts follow a really simple pattern, which is we load raw memory and then immediately cast it to another type, for instance, an integer. The Rust folks expressed some interest in allowing loads to do the type panning, which would allow us to combine this load bytecast pair into a single load to the target type. So we benchmarked an implementation and found that 1.6% of the old instructions in the old version were bytecasts, and this fold changed the number down to 0.1%. So here are the results with the new folds. We see that the average runtime regression reduces to 0.2%, and compile time stays largely unchanged. So regarding the SIMD Johnson regression in runtime, we investigated and found that it is due to jump threading not able to combine some basic blocks that it could previously. We found out that this is due to LLVM's range analysis not being able to operate on the new byte type, only integers. So extending the analysis to operate on byte types as well would resolve this regression. Lastly, we benchmarked an implementation where we switched an initialized memory to poison and lowered the bit fields through the freezing load. So the average regression and compile time impact here are about 0. And the largest regression we observed was in runtime, I believe John the Ripper, with around 1.5%. We traced this regression back to a loop alignment heuristic, which reacted to some small code changes, not necessarily to our new semantics. So to conclude, we introduced a new byte type and a freezing load. Together, they allow us to change an initialized memory from undef to poison. Also, the byte type fixes some additional issues with LLVM and raw memory semantics, fixing some of the LLVM test suite tests and some miscompilations. Furthermore, it has negligible performance costs. And to conclude, I'd like to mention that we started upstreaming the byte type to LLVM, and the first patch has already landed. So, thank you.
Questions?
This is really cool stuff. When you got to the bit field stuff, I was kind of expecting you to say you were going to load it as a byte and then add byte and an OR operations rather than the approach you took. Did you consider that?
Yes, so the freezing load that we use for to load bit fields is actually a syntactic sugar for what you were mentioning. So a load of a raw memory type, a load of the byte type, and then a freeze, an explicit freeze, and then a cast to an integer. So we believe that if we did introduce those three instructions instead of a freezing load, the IR instruction count would increase for bit fields. So that's why we exposed the freezing load attribute.
Okay, sorry, I meant if you added and an OR to be things that could also take bytes rather than integers.
Okay, yeah. So you mean extending and then OR to also operate on the byte type. Yeah, that's a little bit tough because so bytes can hold both integers and pointers. So the semantics of an and or instruction on pointers are not really defined because pointers have provenance. So we don't really have a good semantics to a concrete semantics to extend those instructions to the byte type. So that's why we didn't.
So strictly speaking, this is semantics change of the current LLVM specification. Have you assessed any thoughts on the impact on the other project which compiled LLM, tried to reason about semantic preservation and stuff like that?
Yeah, I'm not really familiar with, so I can't really say much about it. So yeah, sorry.
I guess maybe more just a remark than a question, but having worked on a verification system that worked at the LLVM level, this was a persistent pain in my ass. So thanks for working on this.
Yeah, thank you.
One last question. Hi, thanks for the talk. If I remember correctly from the beginning, you said that removing undef would fix about, what was it, 18% of miscompilations from the test suite? Whereas at the end you say that your fixes about, or with your changes, about 11% of miscompilations.
Yes.
So what about the other ones?
Yes. So the byte type was like, so the initial goal of the paper was to fix the raw memory issue in LLVM. So one consequence of the byte type is that we can also model the bit field loads, which is one of the main obstacles to remove undef. So these tests that I mentioned on the byte type, they are not included in those tests that would vanish if undef was removed. So they tackle things like unsound mem copy lowings and unsound pointer coercions. So we actually haven't removed undef yet because we need the freezing load as well, and we started upstreaming the byte type. So those tests are only concerned things like unsound pointer coercions and raw memory accesses. So those are meant to be fixed with the next patch, which would tackle the mem copy lowering. So yeah, in the long term, those 18% would vanish, yes.
Okay, let's thank Pedro. Can the next speaker come up? Here.
Our next speaker is Renee, who will tell us about the downgrading semantics of memory safety. Can you try speaking?
Yep. All right, thank you very much. So this talk will be about memory safety, or rather providing a semantic framework for thinking about memory safety. It will not be about memory safety in C. It will be about using ideas and techniques from secure information flow to define what memory safety means for small programs written in a small memory unsafe language called NOTAC, with a flat memory hierarchy, integers for pointers, manual memory management using malloc and free. So let's look at a small example. This small program allocates 128 bytes, or tries to allocate 128 bytes. It then proceeds by dereferencing the first of these allocated addresses and printing the content at this address. So is this program memory safe? No. First of all, the allocation might actually fail, right? So in that case, malloc returns a null pointer. And this null pointer may then be dereferenced, leading to a null pointer dereference, which may then lead to a segfault, and so on and so forth. Second of all, even if the allocation is actually successful, the output of the program still depends on uninitialized memory. Of course, the newly allocated memory may or may not be initialized. That actually depends on the implementation of the allocator. So I hope we can agree that this is definitely memory unsafe, but that of course begs the question, what does it mean to be memory safe? And if we look in the literature, memory safety is often, not always, but often defined as a long list of bad behaviors, errors, error classes that should be avoided, that should not occur in a memory safe program. So things like buffer overflows and use of uninitialized memory and so on. So if you want to prove that your program is memory safe, you would have to separately prove that it doesn't have any of these errors or error classes or bad behaviors. And of course, this is far from ideal. In fact, as noted by Michael Hicks back in 2014, actually this goes back way further, of course, but on his blog in 2014, he noticed that it would be really nice to have a definition of memory safety that would rule out these errors, bad behaviors as a consequence of the definition, rather than as building it into the definition. So let's explore that a bit further with the next example. So this example allocates two small buffers, 8 bytes, something like that, and then compares the actual addresses returned by the allocators, right? Depending on those actual addresses, it'll print either a 1 or a 0. So this program doesn't have any buffer overflows, it doesn't use any uninitialized memory, it doesn't have any use after free, and so on and so forth. So by this, by the traditional definition, this would be a memory safe program. However, the observable output from the program actually still depends on the actual allocator implementation. As I just mentioned, it actually depends on the concrete values, the concrete addresses returned by the allocation. So that means that the thing, if we wanted to reason about the behavior of this program, that would actually be really hard if we wanted to do that without taking the allocator implementation into account. So if we wanted to reason about the behavior of the program, we also need to reason about the behavior of the allocator. And we think that, that for a memory safe program, we shouldn't really have to reason about the allocation. We should be able to reason about the program at a sort of an API level instead. So that leads to the sort of the key idea of our paper is that a memory safe program is really a program that doesn't depend on the implementation of the allocator that it's using, right? So how do we formalize this, and how do we reason about this kind of independence? Well, that's I think the key insight of the paper is that we can look to the rich literature of information flow security and then borrow everyone's favorite security property, non-interference, right? Non-interference has been used for literally decades, reasoning about how program behavior, observable program behavior, is independent of any secrets held by the program. So we want to tap into this literature and then think of allocators, or rather allocator implementations, as secrets. And we don't want any of these secrets to leak into the behavior of the program. So we want to show some kind of non-interference result for programs. All right. So how does this look? Again, non-interference is about observable behavior that should not depend on something, secrets or allocators or whatever. So on the right-hand side, we have a small program that does an allocation and then immediately prints the address that is returned by the allocator. It doesn't really matter if it's the null pointer or not, it's just it's printing the concrete value, and this corresponds to a direct leak in the information flow security sense of the word that we have on the left-hand side, where the secret that is input from Alice is directly sent on to Bob, so Alice's secret is leaked directly to Bob. Yeah? Slightly more complex example. So this is the example from before. We have on the right-hand side, the control flow of the program depends on the actual addresses returned by the allocator. So here we have some kind of indirect dependence, right? This change in control flow is observable by the program, by the observable behavior of the program. This corresponds to an indirect flow in the information security world, where on the left-hand side again we have the control flow of the program actually depends on the values of the secrets, and this change in control flow is observable by an attacker by just looking at the output, right? So finally, a non-example, because now we have on the right-hand side, it's a slight change from the program before. I don't know if you noticed, but now this program on the right-hand side, it prints 1. No matter what is returned, no matter what the result is of this comparison of the addresses, the observable behavior is the same. And of course, we want our notion of memory safety to be precise enough to actually capture this as a memory safe program, right? So this is what makes our definition semantic. Also corresponding to exactly the same semantic notion on the information flow side, where again, yes, technically the control flow depends on the secret values, but the observable behavior actually doesn't. So we consider this to be a secure program and a memory safe program, respectively. All right. So now that I have hopefully convinced you that allocator independence is quite useful and probably a good idea for talking about memory safety, let's see where it doesn't work anymore. So on the program on the top right-hand side, we have a program that allocates probably a large buffer or something like that. And of course, this may fail, just like any memory allocation. But this program does the right thing. It checks whether or not the allocation fails. In that case, it prints an error message. Otherwise, it prints OK and is on its merry way. So this is obviously not an allocator-independent program, because depending on the concrete values returned by an allocator, it will either print an error message or it'll print OK. However, we consider this to be a memory-safe program. We really like, for our definition of memory safety, to also include this kind of programs, because we don't think of out of memory as necessarily a memory safety issue, especially not if it's handled correctly in the program. So how do we weaken our notion of non-interference just enough to actually capture these programs, but not any of the unsafe programs? Another example is the lower one on the right-hand side, a small program that, again, it allocates some memory, then it casts the pointer to an integer and prints the integer. Clearly not an allocator-independent program. However, if you're programming low-level systems like device drivers or for embedded systems, you very often have to work explicitly with specific addresses, right? So maybe you're doing memory mapped I/O, or you're setting up interrupt tables or whatever. So again, we would like for programmers to be able to slowly, gradually, in a controlled manner, break this independence. So make the program enable the programmer to say, yes, I know I'm introducing a dependence on an allocator. However, I know what I'm doing, so go away. And of course, still have, yeah, that's naive, I know, but at least we should allow them. But still retain memory safety, allocator independence for the rest of the program. So how do we manage this kind of weakening of our property? Well, again, we look to the information flow security community and look at the concept of declassification or downgrading. So non-interference says that a program's observable behavior should not depend on any secrets unless they have been declassified, because then they are no longer secrets, of course. So this idea of managing and controlling when and where to actually declassify, and of course there's a lot more to declassification, I will not go into that. But the idea here is that we're going to consider the cast to be a declassification operator. So this allows the programmer at least to manage when and where to weaken the memory safety guarantees, and sort of in the same way also for the out of memory. Right. So with all of these puzzle pieces in place, I'll introduce the NoTag language in a slightly more formal way. So it's a small while language. It doesn't contain any real surprises. It's C-like. Of course, it is not C because we don't have any undefined behavior as such, and we don't want to get into that discussion at all. That's not what this is about. But provide a framework for talking about memory safety in a slightly wider context. So the only thing we've added and observed, this is just a way of encoding the observable behavior. So this generalizes the prints and the outputs and network communication, whatever you need. Cast is basically a no-op, is a no operator, and this is actually also the same in the information flow security community. A declassification operator, it's useful for indicating this is where it happens, this is where stuff happens, but it is a no-op in a semantic sense. Our language is, of course, parameterized on an allocator. Allocators define the semantics or implement the semantics for free malloc and then the null pointer, the exception pointer, right? So what is an allocator? In our setup, it consists of 5 things. It has an abstract allocator state. We don't really require anything of this state or have any constraints for it. It's up to the allocator to decide what to use it for. We just make sure to actually thread it throughout the semantics so that it's available. And then, of course, it defines a null address, malloc, and free, and also an initialization that is only run once at the beginning of the program to set up the initial allocator state. Okay, semantics. Nothing too exciting. I'll not go into any depth with that. Just note that the semantic step relation, of course, depends on an active allocator. That's the alpha on the left-hand side of the turnstile. We thread, as I said, the allocator state. That would be the capital A and the A prime. And finally, running the semantics generates an event trace. Events are the things that might happen during execution that are of relevance to our memory safety. So that would be all of the normal memory management instructions. Do note that there is an mfail, which corresponds to, okay, I've tried to do a malloc, but it failed. I tried to allocate n, size of n, memory allocation of size n, but it failed. So we want to keep track of that, of course. And the ops v is, of course, sort of the event corresponding to an observe instruction, right? So these are the externally observable this is the externally observable behavior of the program. So running a program gives rise to an event trace, and this is really what is at the heart of our formalization. So how do we formalize this kind of non-interference? I'll not go into a lot of depth with that, but we'll be more than happy to talk about this after the presentation. We use an epistemic approach, so that kind of turns the idea of thinking about non-interference on its head, if you're not used to it. So instead of thinking of what can be observed, we're actually thinking about what does an attacker know? What is the precision of the knowledge that an attacker may have about the system? In our case, what we are thinking of is what is the set of allocators that would give rise to the same event trace for this program. So basically, this is the set of allocators that we can't really distinguish based on the traces that we've seen so far. Yeah. So the idea for memory safety would then be this set of allocators should be, if not constant, it certainly shouldn't become smaller over execution time, right? So the more we observe, it should stay the same or certainly not grow smaller, because if we can remove an allocator from this set, it means we've actually introduced a dependency, because now we know that it cannot no longer be this allocator. Formally, we define the allocator impact. This is the blackboard A for a command C, for a program C that generates a trace T. So imagine we've run the program C and we've observed the event trace T. Now the allocator impact is the set of allocators that would have given rise to exactly the same trace, basically. Okay? So now, as I said, the idea is we want to make sure that this doesn't really change. That's fine, but we also need to take care of our downgrading operation, so in this case, the cast operation. In order to do that, we rely on some fairly, sort of a weakening of the idea of an allocator, of the allocator impact. So we're going to define this blackboard A, cast, arrow, whatever, to mean more or less the same as the allocator impact, except that it's the set of allocators that would give rise to the same trace, but also furthermore allows for a further cast operation, for a further cast instruction. We make no requirements of what are the addresses that gets cast, so what are the specific values used, but it should be possible to do a cast after having produced the trace T. Same goes for the allocator. So how do we use these allocator sets to actually define the non-interference? Well, if we start from the bottom, that's probably the easiest. So the blackboard A, so the allocator impact for the trace T eta, right? So this is the set of allocators that are able to actually produce the trace T, combined or followed by a single eta event. This should be the same as the set of allocators that could produce the trace T. So what that means is that even though we've seen yet another event, we've observed something about the program, this eta, we can't actually remove any of the allocators from the allocator impact sets, meaning we haven't introduced accidentally or on purpose any dependencies on any of the allocators in this set. Yeah. For the cast operation, this is slightly different because we have to take a slightly weaker definition. So what we're requiring here is that the allocators that have given rise to the current set of traces must be part of, again, this progress impact for cast, which says that yes, it's the same allocators, but all of the allocators in this set must also be able, so all of the allocators that have been able to produce the trace T must also be able to produce some kind of cast operation. Again, we make no requirements on the values that are actually cast or the addresses that actually are cast, but they must be able to do a cast operation. I'm running out of time, so I'll just skip this, just briefly mention that we've used as a use case for this idea, we've shown that we can translate the memsafe language of Amorim, Ritchie, and Pierce from their post-2018 paper into our no-tag language and preserve memory safety. So memsafe language is, of course, a language of memory-safe programs. So this translation actually satisfies our gradual allocator independence, i.e. memory-safe. And in fact, the translation of memory programs that are not stuck, so not errors out in some way, they will either be out of memory or they will succeed with the same memory. I think that's all I have.
There's a lot of questions, but I'm afraid we only have time for one or two quick questions. Could you get set up?
Thank you. I guess it'll be really quick. Hi, I'm McKenna McCall at Colorado State. I'm just kind of curious about maybe a philosophical question.
All right.
Why think about this from a confidentiality perspective instead of integrity?
That's a really good question.
It feels more like an integrity condition to me.
That's funny. I think more of it as a confidentiality because actually we don't want any information about the allocator implementation to leak into the program. So to me, that's confidentiality, but I think we could equally have formulated it as integrity, actually.
Sure.
Yeah.
Okay. Yeah.
Thank you. Oops, sorry.
Your allocator, as it's currently formalized. Hi, I'm over here.
Hi.
May Milano, Princeton.
Yes.
Your allocator, as it's currently formalized, has a very strong, malloc-style API.
Yeah.
Most allocation that you see in C or low-level code is just immediate values. I'm going to stick something on the stack, and now it's memory. In your formalization, if you were to extend that to handle immediate values and then casting thereof into memory, would those all just be part of the allocator, or would those require a different kind of formalization?
So we haven't actually looked at stack memory or indeed at the sort of sub-object memory safety. I think stack is slightly different. We need a different setup for it. I think the basic idea is the same, but we need to identify more places to apply this declassification. because actually I think there is something when we copy things into the stack that would correspond to some kind of declassification operator. But this is very much work in progress.
Okay, let's thank Renee and take work with the So our next speaker will be Anna, who will be telling us about causality and semantic separation.
Hello, okay, thank you. I'm Anna. I recently finished my master's in CS at MIT, and today I'll be talking about a semantic characterization of deseparation. So this work lies at the intersection of programming languages and causal inference. Our goal is to give the standard graph analysis in causal inference, which is called deseparation, a formal semantic characterization, analogous to how program analyses are justified by semantics in PL. So this is important because a formal semantic characterization can explain precisely what property deseparation is actually capturing and why its graph rules are correct. Let me first give a brief intro to causal inference. So it is the framework used to reason about cause and effect relationships and to design experiments. So it studies whether variables are causally related and whether an experiment could identify those relationships, perhaps after conditioning on other variables. The key object here is a causal model, which is a DAG describing how variables could potentially influence one another. So in the example on the right, we have the node prior knowledge being able to affect study time as well as test score. And we might wonder whether the amount of extracurriculars that one participates in can have a direct effect on test score after maybe we condition on study time and prior knowledge. Now, deseparation is a purely graph structural criterion, and it determines exactly when variables can influence each other after conditioning on other variables. And so this question could be rephrased to, are extracurriculars and test score deseparated, conditioned on study time and prior knowledge? And this is equivalent to the widely known notion of conditional independence. So from a PL perspective, deseparation looks a lot like a static analysis. It determines what influences what based on graph structure alone. However, it's lacking a formal semantic characterization. And so we introduce semantic separation. We prove that it is equivalent to deseparation, and we fully mechanize the whole development in ROC. This lets us interpret deseparation using concrete behavior rather than graph structure alone. It also provides an experimental interpretation of the predictions given by deseparation, which we'll see towards the end of the talk. So now I will describe how to determine deseparation. The basic idea is that influence propagates along paths in a graph, and conditioning can either block or open those paths. And then two nodes are deseparated, conditioned on a set of nodes, if all paths between the two nodes are blocked by nodes in the conditioning set. And again, this is commonly used in causal inference, in experiment design, to determine what variables need to be controlled for. So our example here contains the three ways in which a path of three nodes could be oriented. And as I go through these three rules, try to notice how they are asymmetric and as a result, maybe unintuitive, which motivates our semantic definition. So in the first case, we have influence flowing through S, and so conditioning on S blocks that influence and blocks the path. In the second rule, we have a common cause of S and T, and so conditioning on that common cause also blocks the path. In the third case, which is the unusual one, S here is called a collider, and S actually blocks the path by default, but then conditioning on S creates a dependency between its parents. This third rule is also more complicated than what I will put on the slide. It's also the hardest to explain semantically. So much of the subtlety of our semantic definition comes from trying to explain this behavior. Now going back to our example, if we condition on study and prior knowledge, we can use these rules to determine whether extracurriculars and test score are deseparated. So by the first rule, the path E to S to T is blocked, and by the second rule, the path E to S to P to T is blocked. And so E and T are deseparated, conditioned on S and P. Now, what's interesting is these three rules completely determine deseparation. And you might be thinking it's not super obvious why they correspond to causal influence in the underlying graph structure. And so we found ourselves asking, why are these graph rules correct? And what semantic property are they actually capturing? So we set out to define a semantic version of deseparation. At first glance, it might seem natural to define the semantics using probability distributions, since deseparation is often presented via its connection to conditional independence. However, deseparation itself is purely graph theoretic. So whether two nodes are deseparated depends only on graph structure, and we therefore thought that our semantic definition should also depend only on structure and not on any particular distribution. So far, we've been treating causal models as graphs, but now we need a semantic representation for those graphs and a way for nodes to obtain their values. Fortunately, we can use the standard model in causal inference, which is called a structural causal model. Think of each node as having an associated function which computes the value of that node from the values of its parents. And so, for example, the function for study, or S, could look something like this. But this model, as I presented it, is a little too naive because in practice, we can never realistically model everything that affects a variable. So for example, study could maybe also be affected by course load or stress level or other factors that we did not record. And so the model introduces an additional input to every node's function. This is called an unobserved term, and they're shown here in gray with an arrow to the specific node that it corresponds to. And so the function for study could additionally rely on its unobserved term, which is U of S. Now notice that once we fix an assignment of unobserved terms, the entire model becomes deterministic. So every node's value is fully determined by just repeatedly applying the functions throughout the graph. So then we can think of a world as just a particular assignment of those unobserved terms. And by changing those assignments, we can compare and reason about different worlds. So we're now going to define the semantics of two basic operations that will be useful in our semantic definition. First, what does it mean to condition on a set of nodes? So it simply means we'll restrict our attention to worlds where the values of those nodes match their target values. For example, in this graph, if we think of prior knowledge as being measured as the amount of material that one already knows on a scale from 0 to 1. Then if we want to condition on prior knowledge equaling, say, 0.2, then any world that properly conditions on P is just one in which f of P equals 0.2. And in the case of this graph, that depends only on U of P. Now we need the notion of changing a variable. So we say to perturb a node means to modify the unobserved terms in a controlled way to change the value of that node, and then observe how those changes propagate through the graph. So for example, if we want to change the value of extracurriculars, maybe from 3 to 4, we would start with modifying its unobserved term, changing the value that we want, and then this can propagate and affect downstream variables, study and then test score. So recall that earlier we were interested in, if we condition on study and prior knowledge, whether extracurriculars and test score are deseparated. Now that we've defined the semantics of conditioning and perturbation, we have a way to ask a more semantically precise question that kind of sounds like the deseparation of two nodes, which is, if we perturb the first node, in this case extracurriculars, while maintaining conditioning on the condition set, can we force a change in the second node, in this case, test score? So we'll now attempt to define the semantic separation of two nodes, x and y. The simplest idea is change the unobserved terms in a way that affects x and see whether y changes. But this is too permissive because it allows for changes that are unrelated to the causal structure. For example, say x and y are completely disconnected nodes. We would expect for x to never be able to affect y. But if we happen to change the unobserved terms of both x and y, then y can be affected by a change having nothing to do with x. So we need to restrict our attention to the unobserved terms of nodes that can actually affect x, which leads us to think about ancestors, since recall that a node's value is computed using the values of its parents. So we will restrict changes to what we call unblocked ancestors of x, which are ancestors that have a path to x that does not go through a conditioned node. This captures causal structure better, but it fails in collider settings where conditioning can create dependencies that are not captured by ancestry. So for example, if this middle node here, w, is the XOR of its two parents, and we want to condition on w equaling 1, then we would expect for x and y to not be semantically separated, because say if we wanted to change the value of x to 0, the value of y would have to change to 1. But this is not captured by the unblocked ancestors method because we can only change ancestors of x. And so if we change the value of x to 0 using its ancestors, that will propagate, and the value of w is now no longer properly conditioned, so the whole system doesn't make sense. We might then attempt to enforce an additional repair step where we allow the changes to propagate, which could affect the conditioned variables. And then we allow for an additional step of repair where we make the required changes to recondition those variables. Here's an example of when we might actually need repair. So suppose we're interested in whether a drug affects reaction time. And we know that this drug affects blood pressure, which affects reaction time. And so in order to isolate the effect that the drug has on reaction time directly, we condition on blood pressure. Then once we administer the drug, we could affect a subject's reaction time. So we might use some other common well-known drug for blood pressure to counteract that effect. So that's us propagating the change that the drug made and repairing the value of the conditioned variable. But this still doesn't quite work in the case that there are multiple conditioned nodes where one repair step might not be sufficient. For example, suppose we have another node, sleep. We know that the blood pressure drug causes extreme sleepiness, and sleep also affects reaction time. Well, then we also need to repair sleep. And you could, of course, imagine we had several more nodes that are conditioned on and would need to be repaired. So this kind of suggests that semantic separation cannot be defined as a single-step notion. It should instead be a multi-phase process. So the fix for this is to allow for a sequence of worlds which represent step-by-step modifications. So our final definition has three main ingredients. First, a catalyst step makes changes to the unobserved terms that are allowed to affect x. Next, we let those changes propagate through the deterministic functions of the graph. And third, if any conditioned nodes have been disturbed, we allow changes to repair them using their own unobserved terms. And then we go back and forth between the propagation and repair steps, since each repair could itself need to propagate and could require more repairs. This results in a sequence of unobserved term assignments, where each pair of consecutive assignments we constrain in a way that guarantees that we make changes minimally. At the end, we compare the original and the final worlds. And if every valid process that changes x leaves y unchanged, we say that x and y are semantically separated. Here's an example from the previous slide where we are conditioning on blood pressure and sleep. So we can show that drug and reaction time are not semantically separated by showing some process that perturbs the drug node and as a result, the reaction time node. So to perturb the drug node, we would have to use its unobserved term that can propagate to affect blood pressure and reaction time. But since blood pressure is a conditioned node, we can repair it using the blood pressure drug. That can propagate to affect sleep, which is also a conditioned node, so we can repair that, maybe with caffeine, and that can propagate to affect alertness and then reaction time. So since we've now changed the value of reaction time, drug and reaction time cannot be semantically separated. And what we fully formalized and proved in ROC is that the notions of semantic separation and deseparation are exactly equivalent. Very briefly, the proof idea for this is to take the contrapositive in both directions. So in the forward direction, we assume that the two nodes are not deseparated, so there exists some unblocked path from x to y. We then construct functions for each node and a sequence of assignments that propagates a change from x to y along that unblocked path. In the other direction, we assume that the two nodes are not semantically separated, so there exists some functions and unobserved terms that propagate a change from x to y, and then we show that there must exist an unblocked path along which that change is actually propagating. So hopefully this slide gives you a flavor of the definition and the proof, but it's of course missing a lot of detail, so if you're interested, please check out the paper and the code base. Now that we have the theorem, here's one way in which it could be applied in an experiment design context. So in a scientific experiment, a causal model is used as the hypothesis of relationships among variables. And so by our theorem, if a causal model predicts that two variables are deseparated, then no valid perturbation of one could affect the other. And if such an effect is observed experimentally, then the model and the hypothesis have been falsified. So here's an example. Suppose we hypothesize that drug has no effect on reaction time after we condition on blood pressure. Now we've turned a graphical property into a testable prediction, which we might test out by repeatedly recruiting new subjects, administering the drug, and then repairing any effect that this has on their blood pressure using the blood pressure drug. Throughout this process, we should observe no change in the subject's reaction time, but if we do, then the causal model and our hypothesis encoded by it have been falsified. So yeah, that's one way in which the theorem can be applied in experiment design, but more broadly, this work introduces a semantic characterization of deseparation, proves their equivalence, and fully formalizes the whole thing in ROC. Yeah, the URLs to the code base and the paper are available here, and I'm happy to take any questions. Thank you so much.
Questions?
Very nice talk. I am Xin Zhang from Peking University. So from my understanding, this operation can be applied to long causal models, like just a regular Bayesian network. So can your framework be the extent to this case?
Yeah, I think deseparation can be applied in lots of contexts, not just experiment design. This work is kind of the foundation in maybe a longer term project to formally verify experiment design. And so I was more interested in using it in experiment design contexts. But yeah, I think it could be applied in other uses of deseparation as well.
Okay, thank you.
All right, in the interest of time, I think we'll take any further questions offline. Let's thank Anna. All right, so for our fourth talk of the session, Tryon will tell us about hyper-separation logic. Are you connected?
Test. So, hey everyone, I'm Tryon. And today I'll be talking about hyperseparation logic, a joint work with Peter Müller and Thibaut Dardinier from ETH Zurich and EPFL, and I'm from Insight. So the goal of this work is to develop the first framework for modular reasoning for hyperproperties. What are hyperproperties? Well, hyperproperties relate multiple program executions together and characterize program behavior by doing so. For example, non-interference relates two program executions universally, that's why two universal quantifiers, and it states that for any two executions, if they have the same public inputs, then they must have the same public outputs. That is, there is no leakage of secret information. Another interesting hyperproperty is generalized non-interference, which is a weakened variant of non-interference to account for non-determinism. Its type is for all exists, which means that the hyperproperty states for all two executions, there is a third execution for which the three executions satisfy some relation. So the type shows how complex a hyperproperty is. And there are many other hyperproperties of interest. On the other side, we have separation logic, which is the gold standard for modular reasoning. Separation logic allows us to prove local specifications, and by applying the frame rule, allows us to augment set specification with an additional heap. However, separation logic is limited only to functional correctness, and the goal of this work is to lift the reasoning to arbitrary hyperproperty while preserving modular reasoning. Now, let's look at some existing program logics for hyperproperties. The most basic hyperproperty is for all hyperproperty, where the logic we all know is Hoare logic. For heap manipulating programs, the standard logic is separation logic. For exist hyperproperties, the two standards are incorrectness logic and incorrectness separation logic, and so on and so forth. Recently, 2 years ago, hyper-Hoare logic was introduced, and it filled a gap for complex hyperproperties by the novelty of tracking set of states instead of simply states or key tuples of states. We'll talk about why set of states are so expressive in the next slide. However, there was still a big gap which we filled with this work, which is for complex hyperproperties for heap manipulating programs. This is where hyperseparation logic comes. Okay, so it's important here to note that hyperseparation logic allows us to reason about different hyperproperties under the one singular framework. For example, if before we wanted to reason about for all and exist hyperproperties, we needed to use two different frameworks. Now we can do that with one singular framework. Okay, now why set of states are so powerful? Consider the following hypertriple, which has the precondition and postcondition colored in blue just for readability. So in our case, the pre and post conditions are satisfied by a set of states and not simply states. So our precondition in this case is satisfied by those set of initial states where all initial states sigma satisfy that x points to 5 and disjointly y is allocated. Then if we execute the program that at y we assign the point at x plus 1, then we end up with a set of reachable states where all these reachable states satisfy that x points to 5 and y points to 6 and they're disjoint. Now if we look at the following separation logic triple, which is the same as the above, but without the universal quantifier, it turns out these two have the same satisfiability. That means that we can express separation logic by just putting an extra universal quantifier. Now, if we look at the existential case, for example, here the precondition states that there exists at least one state sigma, which has R allocated. Then if we non-deterministically assign at R integer between 1 and 4, then it is clear that we will have at least one reachable state sigma prime, with R still being allocated, but now pointing to 1. Without the existential quantifiers, we obtain exactly the validity of separation sufficient incorrectness logic. And for those of you who don't know, SSIL validity states that for all initial states, there is at least one execution trace that ends up in the postcondition. Yeah, so we can express SSIL with one existential quantifier. Now, let's consider the following relational separation logic triple, which expresses non-interference. For L being low sensitivity variable and H being high sensitivity variable. So RSL works just as normal separation logic, but for pairs. So we track pairs of states and not simply states. Here the precondition states that we start with the same low variable L, both first and second coordinate have L pointing to the same value, and we end up with the same value for O. That means that O doesn't depend on the secret H, which is exactly non-interference. We can express this RSL triple with the following HSL triple, where the precondition states that for all two initial states, sigma 1 and sigma 2, they both have L allocated, and moreover, it points to the same value n. Now we execute the program, and our postcondition states that for all reachable states, sigma 1 and sigma 2 primes, they both have O allocated and pointing to the same value. That means O doesn't depend on the secret H, it depends only on L, which is exactly non-interference. So in short, why set of states are so powerful? Because we can put restriction on this set of states in the form of quantifiers, and by doing so, we can express different logics, and even more, we can express hyperproperties which are not expressible by any current separation logic. For example, exists for all. Now, onto the key result of this work, the generalized frame rule. The key new thing is the new hyper-separating conjunction, which we'll denote with the following symbol. Before we see why this frame rule is so general, let's first see this restriction that we have here. We restrict that our frame should be consisting only of universal quantifiers, so no existentials. Why is that? Well, because an existential in the frame would enforce reachability in the postcondition, which in turn enforces termination. That's not that interesting. We will see that this is not a bad restriction. Now, why do you call it generalized frame rule? Well, because using our frame rule, we can obtain the frame rules of other separation logics and even more. For example, consider the following hyper triple, which states for all states sigma, so for all initial states, if they have x allocated and pointing to 5, and then we increase it by 1, then obviously all states will have x pointing to 6. Now, if we frame the green frame that states that all states have y allocated by properties of our hyperstar, which we'll see in a moment, in a sense, our hyperstar distributes over universal quantifiers just as normal conjunction distributes over universal quantifiers. Yeah, we obtain this. And now if we look closely at the top and the bottom part, this gives us exactly normal separation logic frame rule. That is, said concisely, we obtain separation logic frame rule by framing one universal quantifier. We obtain a frame rule similar to RSL for two universal quantifiers. For SSIL, we don't frame with an existential because the two witness executions might be unrelated. This is a bit technical. The important part is we obtain SSIL frame rule by framing one universal quantifier, which is exactly what our frame rule allows us, which is what I meant that our frame rule is, yeah, that this is not a big restriction. However, as I said, we go beyond existing frame rules. For example, the following hyper triple above, expressing that exists for all hyper property, we can, for example, frame for all frame. And what is even better, we are not forced to frame the same amount of quantifiers on the left and on the right, which crucially allows us to frame, for example, non-interference to generalize non-interference, which is exactly what our goal was, to obtain modular reasoning for hyperproperties, and so on and so forth. Now, the key challenge of this work is defining the hyperseparating conjunction. To see how we do it and why it's challenging, let's first consider the normal separating conjunction. P star Q, we all know, is we take all states from P, all states from Q, and if they're compatible, we combine them. So different separation logics have different type for this sigma, and different type requires a different definition for this combination predicate. So separation logic, incorrectness separation logic, and SSIL, the combination predicate for them is just disjoint union. For relational separation logic and other such relational logics, the combination predicate is just pointwise lifting of the disjoint union. That means first coordinate with first, second with second, third with third, and so on and so forth. However, for our case, it's not that simple. Why? Well, because we don't have ordering. We cannot do first with first, second with second. Sets don't have order. Second, the cardinality of the two sets could be different, and on top of that, one could be finite, the other could be infinite. It's not a trivial task to define this combination predicate. And yeah. So now to gain a bit of intuition about this combination predicate, let's look syntactically the following assertion. The assertion says that all states sigma have X allocated. Now, if we disjointly add to it that all states have Y allocated, intuitively this should be equivalent to the fact that all states have X and Y allocated and they are separate. So, as I said earlier, in a sense, the hyperstar distributes over universal quantifiers, just as normal conjunction does. But it is separating. For the existential case, if we have that there is at least one state with X allocated, and we add to it that all frames have Y allocated, intuitively this should imply that there is at least one state with X and Y allocated and they are separate. Y implication and no B implication, because on the left we have that for all states Y is allocated, while on the right we have guarantee only for the witness state. So, in short, our hyperstar should respect both universal quantifiers and existential quantifiers, just as normal conjunction does. The only extra thing is that it should be separating. With that said, we proceed to defining the combination predicate. Consider the following set of 4 states, in this case, SP, where circular sectors represent heap, so the bigger the sector, the bigger the heap. And cores represent stores, so different core, different store. What does it mean to disjointly combine it with the following set of 3 states? Does it make sense to equate this set of 1 state? Well, consider that SQ satisfies that all states have Y allocated, and let's say that this is the part showing that Y is allocated. As you can see on the right, Y is not allocated, but we said that our combination predicate should respect universal quantifiers, and it doesn't here because we don't have Y on the right. So we should refute this S. We do that formally by the following. We require S, the one on the right, to be a subset of SP normal star SQ. By doing so, so that means that all states in S should be at least as big as the states in SQ. But as we can see, this state in S, the green, is not as big as the green state in SQ. So we correctly refute this S. What about the following S? Now we can see that the universal quantifier is indeed respected, but what about the existential? Let's say SP on the left satisfies that there is at least one state sigma with X equal to 5. And let's say that the blue color represents that X is equal to 5. As you can see on the right, we don't have blue color. That means that, that means that the existential quantifier is not respected, so we should refute that, because as I said, the combination predicate should respect also existential quantifiers. We formally do that by requiring the following predicate, PLW, which stands for preserved left witness. And it states that all witnesses on the left, so SP is on the left side of the operator, So all witnesses on the left, so the blue state, should be preserved through a state on the right, so the blue in SQ, into S. Because now we have preserved the witness, that means we respect both universal and existential quantifiers, so this S should be accepted. And we have a symmetric preserved right witness if the existential quantifier was on the right-hand side. Okay, with the main contribution covered, we now turn to the smaller contributions. So first thing, we identify and solve two non-locality problems. That means two problems with the frame rule. The first one is about allocation, and the second is about errors. And for errors, we identify two types of errors: local, which means compatible with the frame rule, and non-local, which means non-compatible with the frame rule. We solve the problem with the non-local errors with the so-called unknown states, which unfortunately I don't have time to tell you more. Then we define hypertriple validity and prove semantic rules sound, which is what we call hyperseparation logic. And finally, we define a syntax for our hyperassertions and prove syntactic rules sound, which is we obtain a syntactic variant of hyperseparation logic. There is one more thing that is novel, is the so-called scaffold variables, which greatly eases the work with our syntax, and moreover, it allows for a stronger read rule, which is quite technical, but it's very interesting. And we formalize all of this in the proof assistant Isabel. And with that, I'll finish and give time for some questions. Thank you.
Questions?
Okay, so this is very cool. I'm curious about what sort of future work is going on.
I didn't hear what?
Future work.
So future work is concurrency and non-termination. And relational properties, yeah.
Hi, thanks for the talk. So if I understood correctly, like all the examples you showed, the resources in the separation logic were plain regular heaps. So I wonder how much of this generalizes to arbitrary PCMs, or like did you use extra properties of the heap that go beyond the basic PCM axioms for this?
So I believe that this general idea would hold for any type of PCM, because I don't show here, but there is this PLW and PRW actually stand for, they correspond exactly to subtraction, which in a sense lift us away from the concreteness of the model and just steps on top of the normal separating conjunction. So for whatever the normal separating conjunction works, the hyper separating conjunction should also work, just because it's very abstract. It steps on normal separating conjunction and normal subtraction.
Okay, cool, thanks.
Hey, thanks for the great talk. So maybe a kind of general question that would maybe apply to hyper-Hall logic as well. So if sometimes hyperproperties are used to reason about two programs at the same time, for example, when you do refinement. So could you extend that like state-based reasoning to reason about two programs at the same time?
So yeah, this is part of yeah, we are working on that.
So when you mention concurrency, maybe that also
yeah, all concurrency, relational reasoning, and non-termination. Yeah, but each one has their their difficulties. Yeah.
I actually have a question about the frame rule for the incorrectness or the SSIL logics.
Yeah.
It seemed to me, maybe I'm confused, but it seemed like when you're framing on a for all, yeah, there. When you're framing on a for all, it seems like the rule you end up with is not quite comparable to the standard rule in those logics, because there you would have an exist that spans over the entire pre or the entire post. Is that, am I getting that right? Or is
so for separation logic and relational separation logic, we require only the consequence rule. For SSIL, we need one extra step to drop away the universal part that isn't attached to the existential part. So yeah, there we need one extra rule, which is joint true rule. Yeah.
Okay. All right, let's thank the speaker. And can the, oh, we have the next speaker, yeah. Great. Oops, sorry, yeah, this is a hazard. I've tripped over 5 times. All right, so for our final talk of the session, Robin will be telling us about pantomime. Try speaking.
Hello, hello, yeah. This, okay, wait. Let's see. Right, perfect. All right, so let's dive right into it. I'm Robin, and this talk is about timing side channels for hardware, or specifically how to prove your hardware does not have them. So timing leaks secrets. So if you have a computation on which you're computing on some secret, and you observe that this one is pretty fast, and then you're doing the same computation on a different one, and you observe it's slow, well, then an attacker can see if it's fast, which, you know, the yellow secret was used. If it's slow, the red secret was used. And these timing side channels, they're used to break a lot of stuff, including cryptographic code. If you're not careful with this stuff, you'll leak your private key, and this is very, very bad. So one of the things to avoid, for example, is branching on the secret. If you do, the timing depends on whether you took it, because this body takes some time to evaluate. And similarly, if you use a secret to index into an array, you'll leak information because actually an attacker can measure if they have a cache hit or miss at the specific index of the secret. On the other hand, it's completely safe to do addition on secrets because we expect that these additions are constant time for all inputs. And this notion of using these instructions in certain ways or avoiding some is what we call constant time programming. And now we want to capture this constant time policy in leakage description. So this leakage description essentially tells you what an attacker can observe, or in other words, what part of the secret we censor. So you can think of it as redacting, like removing parts of the secret until you give something that an attacker is able to, or that you think an attacker is fine to observe. So with respect to this constant time policy, if you have an addition operation, then we censor out the operands because we're not leaking them. We only leak that we are doing an addition. But if we have a conditional, then all bets are off. We're just leaking whatever is in the conditional because, you know, we can't protect against this. So this is the constant time policy essentially. And now the crypto writers, they just assume that this policy is implemented. But sadly, usually this hardware does not implement it, right? So it should, and I'll emphasize this should because there's a lot of, for example, Spectre-like attacks, which is a type of side channel which uses speculative execution. Like only in the last year already, we have like 9 new variants of these Spectre attacks. So yeah, it's not a given that these hardware circuits actually implement our leakage specification. So the idea is that we want to prove that our hardware does indeed implement this leakage description. And how would we prove this? Well, if we have 2 secrets and they go to the same secret once they're censored, then ideally we want no observable timing difference from our computation. So this is sort of the high-level property. If these secrets censored secret match, then we want the timings of the circuits to match. But it turns out that this proof is pretty difficult in general. So requires usually a bunch of inductive invariants. And the people who want to write these proofs are circuit designers. There are no verification experts, and usually it lies a bit out of their expertise. And then if you're trying to find this invariant and it doesn't work out, you'll get a counterexample that gives you 2 secrets, and then you have to diagnose 4 executions of all of these circuits to actually find out what's wrong. So we propose a different type of non-interference check, which is inspired by cryptography, where you have a simulator which essentially should replicate the timing that an attacker can observe. And it will do so using only that censored bit. And if we actually can find this, if this one exists, then we know that the timing of our original circuit is actually independent of the full secret, because we could replicate it using just the censored version. So using the simulator, our proof goal changes quite significantly. So this is kind of the key thing of this talk, is now we have this timing of the circuit, and we want to censor the secret and show that we have the same timing using the simulator. And if we can show this equivalence, then we're happy, right? And some of the nice properties about this is that the simulator, it's a circuit itself. And the hardware designers that want to prove this property, they know how to write circuits. It's their job. And then if a proof doesn't work out for whatever reason, they can actually run all of the components, right? Because the simulator is just a circuit. The leakage is just a circuit. They can run and debug them with the tools they know. And the counterexamples, there'll be a single secret that's only, of which you only have to run diagnostics for 2 runs of circuits instead of 4. So that's our solution. Now let's do a simple case study of an adder with a fast path to just give a glimpse of what this proof method would look like in practice. So first of all, what are circuits? They're these things that take some input and they produce some output. And they do so using some state. And the state is updated at every clock tick, and they use it for the computation. And well, we're at PLDI, so we could use Verilog to write our circuits, but we're going to use Haskell, because why not? And in Haskell, a circuit definition looks like this, where you have some state, your current state, and an input, and you will compute the next state for the next cycle and output. So before we actually go into writing our adder, there's one quick data type that we use very extensively, so I'll just cover it. In hardware, you don't always, the hardware always runs, but you don't always have something to compute on. So we want to show that sometimes it's fine to have no payload, essentially. So we have this data type that tells us, OK, if there's a jest, we have something to compute on, and we'll do our thing. And sometimes there's just nothing, and the payload is missing. This is also commonly known as an option in many languages, for those familiar. So our adder circuit is a circuit that is this maybe and 2 operands in it, right? The inputs for addition, and we'll we'll compute the sum of these operands and then register the result in our state, which we would then use in the next cycle. So in the next cycle, we simply output the result of this sum, and we'll see that this one has 1 cycle delay, because we use the state to store it. The adder also has a fast path. So if we give it this input, where the first operand is 0, well, then we can simply immediately give you the value b, the other operand. And this one is instant, right? So that's a fast path on it. So this adder has the type signature as below, and we'll give you the definition for it as well. So the adder takes some state and input on which it case splits. If there is a state, we're already in a computation, so we'll ignore the input, and we simply give you that result. If we get a result or an input for which the first value, first operand was 0, we'll take the fast path. Otherwise, we'll compute the sum, put it in the register, which will emit in the next cycle. If there's no input and no state, simply the circuit will be idle, and we have nothing as a return. So how do we model timing? Well, how else than with another circuit? So this observation, this is an observation circuit, and the idea is that you can model timing by using this payload availability, this maybe portion of the type. So this observation circuit is simply a little function that takes out the integer of this maybe type. And now we can run these, of course, because they're just circuits. So just to exemplify, if we give this circuit 3 and 4 to add, then we'll see after emitting the payload with the observation, we'll just get this just unit. And this will happen at cycle 1. So at cycle 0, we'll get nothing because the computation was still pending. Conversely, if we give it the 0 as the first operand, then we'll take the fast path. So we still see this just unit, but it will happen at immediately after no cycles, essentially. So yeah, this fast path leaks. And if our attacker can see that some input took 0 cycles to compute, they'll know sort of this shape of the input. So that leakage is inherent, but it's also not necessarily bad. We can actually still capture this leakage in a contract. So to just reiterate, the final proof goal is that we have this adder with an observation, and we want to show with our leakage that we can actually simulate the same timing. And if these are equivalent, we're happy. So let's define our leakage description, which takes our original secret and it censors it out. And the intuition behind this type is that the maybe tells you whether there's a payload, and the Boolean tells you if the first operand was 0 or not. So it's essentially stateless circuit, so it just passes this unit because it doesn't actually use the state. For the output, it k-splits on the input. If there's an input and the first operand was 0, we'll pass in just true. If the input was there but not 0 on the first operand, we'll pass in just false. And otherwise, there was no input, so we'll simply propagate this. And yeah, this is the final output, so we just propagate this unit together with output. And now, well, the goal was to replicate some timing, right? So if we feed this just 3, 4, as previously into our leakage description, we'll get this output of just false. And now, just to remember what the timing was for the adder, it emitted after 1 cycle. So our simulator simply delays, using this information of just false, it delays the output by 1 cycle. So it emits nothing and then just unit. And these are equivalent, so that's great. And the same happens for this fast path, where we see a different result. And also, this one took less cycles to compute. And the simulator will just immediately give you the result. That's all it does. And these are equivalent. So that's basically it. We've proven that this leakage description adheres because we could show that a simulator replicated all the timings. So yeah, we're happy. So let's quickly look at the evaluation we did for this project. So we wrote this core in Haskell called AIM-core, which is a RISC-V 5-stage in-order pipeline. It's written in roughly 800 lines of Haskell code. And we verified a leakage for this, where the leakage is 300 lines of code, and simulating the timing for this circuit actually is 200 lines. So the verification of this stuff is actually pretty quick. So it only takes 40 seconds to show that there's an equivalence between these circuits. We have artifacts available as well as full code for both the core and the proof tool that we use to show circuit equivalence. Another cool thing is that, well, these leakages are executable. So we can just use them to check whether some crypto library is safe or not. And we ran it on libsodium and wolfSSL. And surprisingly, we actually found 2 CVs or 2 bugs in wolfSSL, which we submitted to them, and they've already resolved these issues. So that's pretty cool. Yeah, of course, it's a short talk, and there's a lot of stuff in the paper. So here's just some teaser of cool stuff that's there that you can read if you're interested. So of course, writing this simulator by hand can be somewhat daunting. So we actually have a way to sort of create the simulator using the already existing circuit. And the idea is to invert the leakage. So pick a candidate of all the leakage inputs, and then use the circuit to actually give you the observation. Actually, we can also sometimes omit the simulator entirely. And we didn't really talk about what property we actually check to prove the equivalence. So there's some interesting stuff here as well, where we make some sort of refinement relation between these 2 circuits. Because actually, they both have like different states, and we only want to actually reason about their outputs being equivalent. And then, of course, so we also created a tool, which is like a Haskell symbolic evaluator to show equivalence between these circuits that we wrote. So this is the takeaway. If you want to do some non-interference stuff and you find this daunting, then maybe try out this different method to prove the same property via simulation, which has some nice properties to it. So here's a QR code to the proof tool and to AIMCore. Yeah, that's it. Thank you.
Thank you, cool work. So with your leakage descriptions being circuits, how do you handle misprediction? I mean, in other leakage descriptions, for example, you have like this always mispredict strategy where you go down both paths of the if, right? To like model that, okay, potentially we might go down both paths in the cache. Yeah. So how do you model that in a circuit?
Well, first off, so we've only proven stuff about in-order circuits, which is pretty much what most work in this area does, or no one has really proven like a out-of-order one. We're working on this, but I guess, like.
Okay, sorry, I didn't want to confuse you. I'm just asking because you mentioned Spectre in the beginning.
No, no, of course. Yeah, I guess like it's definitely our goal to actually prove these things, and I think we can capture also this notion of speculation inside of these contracts. But yeah, it's a work in progress.
Thank you.
Thanks for the talk. This is Rajat from MIT. So actually, the architecture community, they care a lot about this problem, and they can get to out-of-order processors and prove leakage properties about them. They do usually use self-composition, which I think is the first thing you're describing up there. Mm-hmm. I actually didn't quite follow what the verification technique is. Once you have your verification conditions, do you discharge them automatically, or am I writing like a proof script on the side?
There's 2 parts to this. So there's some refinement relation where you show like how the states of these 2 circuits relate. And then at the end, we discharge this equivalence of these 2 circuits to an SMT solver.
And so I give you the refinement mapping?
Yeah, you give the refinement mapping. It's actually, this refinement mapping is also just another Haskell function that maps the states in some way. Yeah.
Thank you.
Any more questions?
Just one more on maybe the usability, or like how do I use the proof tool. If it's, especially that extracting the simulator from the circuit, I suppose this means I need my circuit description in Haskell.
Right, so actually like the proof technique itself also translates to Verilog. So you can just use it in this setting as well. But we've yeah, we've opted to use Haskell for all of these. Has some nice properties, but yeah, the general technique just translates.
All right, let's thank the speaker. It's time for lunch.
Thank you.
Hi, hello. Bruh, it's not coming. This is. This is. Hello. Yeah, this is my voice. Okay.
Hello? Hello? Okay. So, good afternoon, everybody. Welcome to the equality saturation session. And my name is Haobing Ni. I come from the University of Washington, and I will be serving as your session chair for this session. Okay, so we will get started in 2 minutes. And in this session, we have a total of 4 papers, which includes both new extensions to equality saturation engine itself and the new applications of applying the equality saturation technique to new domains. So I think it is very exciting to see both kinds of equality saturation research and see them go in hand. Okay. So let's get started. So for our first paper, I would like to recall everybody that the root of eGraphs lies in SMT solvers. And the application of SMT solvers require you to actually use lots of different versions of eGraphs because you want to explore the space of predicates and you want to try things and retreat back to things. So this paper really gets us back to this old root of eGraphs. And please, so welcome Jadim, and he will explain how you can do that versioning very efficiently for eGraphs.
Thank you very much. This is joint work with my colleagues George Zakur, Pascal Weisenburger, and my supervisor Guido Slavanesky. And in our group, we are interested in program verification. So you would consider a program like the following and prove some properties about it. This is going to be the running example. It's basically a function that is computing the distance between 2 points, given the difference between their coordinates, and some function f, which denotes which kind of distance we are interested in. And particularly, this function is going to perform some optimization depending on the inputs. So if, for example, x is equal to y, we are going to just apply f once. And now, when you're considering this kind of function, you might be interested in properties like, is the distance function actually commutative between x and y, given all these optimizations? And to do that, since this is an equational property, you're going to look at the program and see which equalities between terms hold. So first, you might look at the scope of the programs and notice that some equalities only hold under certain assumptions. For example, x is equal to y, but only in the first then branch, and in the else branch it's actually different. And dx is equal to dy in the second then branch, and it's different in the other else branch. Right. So there are a lot of verification tools that are able to reason about these properties, and most of them rely on an SMT solvers. And the SMT solver itself will rely on a data structure which is called an eGraph, and inside of the eGraph is unified. More recently also, there are solvers that have been implemented directly on top of eGraphs, so automated prover like DESI and CCLemma, which are novel, and we also include those kind of solvers. So today I'm going to talk about union find and eGraphs and some of some extension to reason about conditions and more persistence. So first, let's deal with union finds. And a union find is really a way to encode an equivalence relation. It's basically a graph of nodes that are terms, and if 2 terms are connected, then they're equal. So we are going to consider the union find at point A in the program. And the way we're going to reason about equivalence relations here is we are going to put all the terms that we find in the programs inside the union find. So each term is a node. And now we're going to scan the program to see which equality actually holds. And in point A in the program, we start by saying that dx is equal to f of x. So the way we add this equality is by adding this edge between f of x and dx, and this is called a union, and operates as the root. And then you will discover dy is equal to f of y, and dx is equal to dy at point A in the program. Notably, the fact that the union only is only adding edges at roots. It means that actually the union find is not a graph, but it is a forest, and the forest is basically containing an equivalence class of terms. In this case, there is an equivalence class of 4 terms displayed. And moreover, since this equivalence class is a tree, it means that you can select a canonical element of the equivalence class by simply following the edges to the root. In this case, the equivalence class or the representative of the equivalence class of f of y is the dx. And finally, with path compression, you can shorten the path that you follow from the term so that future queries are going to be faster. So now there is a problem with this, with encoding equality in this way, at least like for each branch, and it's basically duplication. So if you were to consider a more complex program like this one, it doesn't matter really what it does, but it basically applies the distance function multiple times. And maybe we want to prove a property of this program, which is, or this function, which is some sort of commutativity of its arguments. Now, for example, we don't know what is AB, so we need to unfold the definition of this to understand what are the possible cases for AB to be. And we are going to see that the cases are the same as before, structured in the scopes. So we have to consider 3 cases. And I'm going to represent them as blue nodes on top of the green tree. And now, when you're going to unfold the second definition, you're going to span the same tree, but for each leaf, which means that you're going to now have to explore 9 cases. And if you keep going like this, you're going to reach exponential explosion. And more importantly, now you have to consider 81 cases, but there are a lot of ancestors in common between these cases, which means that there is a lot of redundant work that is shared. So we need to deal with this shared work, and this is why researching persistent techniques for union finds and egraph is very helpful. And this is, in fact, our first contribution, which is a version union find, which is a simple way to reason about persistent in union finds. So the first thing that we see is that the version union find has the same term space as a union find. So the terms in the graph are the same. But we now associate to each scope a version, which is some identifier, actually, just to recall that specific scope. So for example, x is equal to y in that scope, and that scope is called 0.1. And the idea is that equalities that hold at a certain scope must of course, hold also at inner scopes. And this is basically translated into descendant version are an equivalence relation that is a coarsening of equivalence relation of ancestor versions. So if you have this kind of structure, now you can scan the entire program. And the first thing that you will do is encounter x is equal to y, and you will just perform a union as before. But now you can also label the edge by saying that that equality is actually only valid in the scope, 0.1. So now you can go along with the program, discover new equalities, and these are true, but in a different scope, 0.2. And those that are true in 0.1 are not true in 0.2. And when you find dx is equal to dy, this is an additional scope, which is 0.2.1. And now this union find is encoding all equivalence relations in the same data structure for these programs. Importantly, the equivalence is now basically an extension of connectivity, where you are allowed to follow edges that are either in the version you're querying or in an ancestor. So if you want to find the canonical, for example, of f of y at version 0.2.1, you are allowed to follow 0.2 because it's an ancestor, and 0.2.1 because it's the same version. So this traversal is allowed. And finally, you can also perform path compression by adding this additional edge. And this additional edge is not only shortening the path from the element to the other, to the representative, but it's also making it easier to recognize whether you can follow that edge or not, because you don't have to query whether it is an ancestor or not. Right. So there are a few problems with this, which first is to ensure correctness. That is, as I said, descendant version must coarsen ancestor versions. So I can construct an example like the following, where I'm unioning y and z as a descendant, and then y and x at an ancestor. And now what happens is that I have that x is equal to y at the ancestor, but not as the descendant anymore. So what I need to ensure is that every union at an ancestor actually implies unions as the descendants. So there is some process of propagation. And this propagation will add that additional edge, which ensure actually that x is equal to y as a descendant as well. And another problem with termination, which is actually related. And the problem is that I can construct an example where find doesn't terminate by adding this edge at a descendant. and this edge as the ancestor. And now if I were to query the equivalence class of y as a descendant version, I'm stuck into this loop. And the solution to this is somehow making these loops trivial to detect by maintaining version canonicals. So by propagation, I will end up with a configuration like the following, where I know that there is this self-loop around x, and now when the find traverses a self-loop, I know that I've reached the canonical for that specific query. And another way, one way to achieve this is by propagation as before, but another way is by full path compression, which achieves this different configuration, but it works all the same. So you can choose which optimization you want to do. Okay, we perform a complexity analysis of this data structure, and the idea is that we simulate a version union find using multiple copies of a union find. So we apply the same operation, but on multiple copies on a union find, and in this way we can extend the classical result by Tarjan. And the basic idea is that the worst case for a version union find is the best case of maintaining that many clones, where that many means the number of versions that you're considering. Which also means that any amount of propagations that you're avoiding, you're achieving better performances. And then when we reason about programs like this list function, we are also dealing with a function like that argument f. And if the functions are pure, then we have to deal with congruence, which basically means that we know that for equal input, a function must produce equal outputs. And the traditional way of doing this is using an E-graph. And the idea is that it's basically a union find where the elements are eNodes, and an eNode is just a function application. And a function application is represented as a function symbol with some pointer to this argument. So for example, you can see the constant x is just the function symbol x applied to the null pointer, and the function application f of x is the function symbol f applied to x. Okay, so if we want to consider the E-graph at point B in the program, now you will discover the equality x is equal to y as before, and you can add it as in the union find. But now the problem is that you have just breaking the congruent invariance because you have equal input x and y, but different output f of x and f of y. So what you need to do is apply rebuilding. And rebuilding is really just unioning and finding. You want to union a node with its canonicalization, which is obtained by replacing its argument with canonicals. And this is a key insight because if rebuilding is just union and find, then we already have all the ingredients to have an version E-graph. And in fact, in a version E-graph, you would add this x is equal to y at a certain version, which is a labeled edge. And then if you want to restore congruence for that version, you're just going to apply the union and define as that version, and you will have the same correctness for the congruence invariant as that version. So if you're going to explore then the rest of the program, you're going to just proceed as a union find in this case, because that is the only case for congruence. So in the paper, we have several artifacts. The first one is a formalization where we define the union find and the E-graph, and we also prove them correct, where correctness means that a user would provide a sequence of equalities in certain versions, and the union find will represent the smallest reflexive, symmetric, and transitive closure of that sequence of equalities, and the E-graph is also the congruent closure. The version union find has also been mechanized in Lean. And the second artifact is an implementation, which is an open source library in Rust, where we support most common E-graph extensions like the fair rebuilding, E-class analysis, e-matching, saturation, and extraction. And the insight is that most of them actually boil down into maintain some kind of version cache. Moreover, recently we explored version proof production, which is to appear as a paper actually in 2 weeks in Very Langetikub. So for the evaluation, we considered 3 case studies, and we compare 4 different approaches. The first one is versioned E-graph. The second one is a naive cloning of E-graphs. The third one is a naive implementation of persistent E-graph, which is basically using existing persistent data structure in Rust. And finally, Easter egg. In the first case study, we consider a parameter analysis where we vary some configuration of E-graphs, and we generate some random E-graphs. So it's a random workload. And we consider 25,000 configuration, and in general, for runtime and memory, we see that we achieve better performances. For the second case study, we consider an EOF solver, where the workload is push and pop, which means that we're going to only work on the leaves, and when we're done working on the leaves, we can also drop them. We consider 6,000 benchmarks from the SMT-lib about EOF theory, and we see that the performances are similar, maybe a bit better with respect to the best approach, which is the naive persistent egraph. And these are way better than the other two approaches. And finally, we consider another domain altogether, which is what I mentioned before, an automated prover called TESI by Singer 21. And this workload is instant concurrent, where the idea is that we want to explore the possibility of working at any version at any time. And we consider the 300 benchmarks from the original paper. And here we perform similar to the best approach, which is cloning, which is way better than the other two. So for the parameter analysis, since I could not pick some precise measurement, I'm going to show the charts. And in the charts, we can see basically on the y-axis the resources for generating a certain configuration in terms of time or memory. And on the x-axis, the number of nodes and unions. We also varied the versions, but I cannot show it in the presentation. So what we see is basically that lower means better, and version egraph is consistently better in terms of time and memory, varying unions and unions. Right, so just to wrap up, in summary, we are interested in program verification, so we are going to consider some programs, and we want to prove some properties about them. And to do that, we are going to deal with equalities, and some of these equalities will only under certain assumptions. Then we provided a new implementation of persistence for union find and egraph, which basically aims to reduce the amount of redundant work between equalities that hold under different assumptions. And then we provide a formalization to prove the correctness of the version of union find and egraph, and open source library with most common egraph extensions. And finally, an evaluation of 3 case studies where we show that we are either better or comparable to the best approach in the state of the art. So if you are interested in looking at the paper, where there will be many more details, you can scan the QR code. You can also find on the top right a link to the artifact and to a Jupyter notebook where there is an easy implementation where you can try it out. So thanks for the attention, and I'm open for questions.
Okay. Thanks, Jetting. And now it's time for questions.
Hello, I'm Adam Chapala from MIT. My understanding of kind of the API of your system is that it lets you track logical consequences in multiple different hypothesis contexts at once, and takes advantage of implication relationships across those hypothesis contexts. But it seems like the only implications you use are those that are present syntactically in say the program that you're verifying. And there could be other provable implications, maybe even some that only follow using information deduced through equality saturation that you're not taking advantage of. Does that sound fair?
I see your point. So I guess what you're saying is something like you might discover that some condition might actually be the same, and maybe you want to share equalities between those conditions, right?
A really basic example would be you just copy and paste 2 versions of a program in a row, and you want to reuse all the work from analysis of the first one for analysis of the second one.
Yeah. I think like I had an idea where you would be able to, actually this is kind of future work, where I wanted the ability to be able to merge 2 versions in such a way that you do not only share among scopes, but also among independent versions that somehow, for some semantic reason, you know that they share something, right? So this is a bit forward-looking, though, like it's work in progress.
Sounds like a great extension to look at.
Yeah.
Thank you.
Okay.
Hey, thanks for the good talk. Max Wilsey from UC Berkeley. Do the versions have to form a tree? Do the versions have to form a tree, or can they be just partially ordered?
Yeah, it's part of this actually. Like right now they are only a tree, but potentially what you could do is, for example, say that you want to union two versions, and you want to consider a new version that is actually inheriting from two, or maybe intersecting two versions, saying, for example, if you want to do a case analysis, you want to only consider facts that hold in any of them, right? In all of them, sorry.
But currently they're just a tree?
Yeah.
Okay, cool.
Okay, I think we can have.
Thanks. So, great talk. So it seems so this work is solving the same problem as the color graph, but it seems yours is better. Is that true? And could you give the intuition for why it's better?
Why it is better? Yes, I can give some observations about what are the differences between other approaches. If I can, it's lagging a bit, sorry. Right, so these are some of the features basically of version eGraph. The idea that we have full sharing between the term space across versions. There is also partial sharing of equalities between dependent version, and this is kind of the scope. And the idea is that right now it's between dependent version, but we want to do it, as I said, between independent versions. Then there is this version path compression, which is actually trading off memory with runtime. So there is a better balance. Also, since you have a view about all the versions that you're maintaining, you can also do better cache management. For example, if you apply equality saturation at a version, maybe you need the cache for that version, but you don't need for another version that you're not considering at the moment, right? Yeah, a bit of the cons is that right now the implementation of this eGraph extension is very naive, and we should probably look into some more version-aware extensions. And yes, of course, it is a bit more complex to achieve parallelism with respect to cloning or simple persistence.
Okay, let's thank Jalim again. Okay, so for our second talk, this is about applying equality saturation to electronics design automation. So in electronics design automation, EDA is a very important problem that suffers from phase ordering between different stages of the compilation. So our next speaker, Jintao, will introduce this work that teaches us how to optimize simultaneously both at high level and low level.
Hello everyone, I'm Jintao from UC Santa Barbara, and I'm going to talk about my, this is a joint work with Sijie on our improving equality saturation for EDA via semantic eGraphs, and here are my collaborators. So we have two contributions, and we introduced a eGraph variant called semantic eGraphs that capture the semantic equality instead of only the syntactic equalities, and we implement a EDA framework called NectMap based on the semantic eGraphs that bridge the higher level and lower level abstraction. So more specifically, at hardware EDA compilation flow, it's word level and bit level, and we run more synthesis passes simultaneously than the previous EQSAT tool. So first, about our motivation. Hardware synthesis is like the compiler for hardware, and there's long passes, a long pipeline of passes. Like there's an open source tool called USys, has around 50 or more passes for one FPGA backend, and all of them are like manually ordered. So there are two kind of passes we are caring about. One is about optimization, which is backend independent transformation, and we also care about the technology mapping, where we want to lower the netlist into the target primitive. We are targeting the FPGAs, so we care about the lookup tables, flip-flops, and DSPs. And the mapping quality influences the quality of results heavily, including the area, delay, and power. And today, actually, the mapping tool is traditional mapping tool is doing syntactic pattern matching. So for the block like DSP, lookup table, and VRAM, they have a hand-coded library of syntactic patterns, and the mapper will pick this pattern. Like only there's a exact syntactic match, we can do a matching here. However, this is problematic, and here is a very common failure pattern. And suppose a previous pass output the expression like 8 multiplies the b plus c. However, the encoded pattern in the DSP library is the sum multiply a. We don't get this DSP mapped, and this will end up in worse performance. So the reason is syntactic matching only matched one form at a time. So this is where the equality saturation comes in. So equality saturation removes the single form limitation. We can maintain all the equivalent expression in the same E-class, and the mapper can match against all equivalent form, extract only once at the end of the flow. However, this is not true between stages, because since this path has a lot of stages, and at each boundary we have to extract one form from the previous stage and hand it off to the next one. For example, we may do the optimization in equal saturation, but hand the result to the separate mapper, and the phase ordering issue returns. So here's an example. Suppose we have, it's the same DSP example. Suppose we have the original eGraph, and we can add a red pro for distributivity, and we're even saturating it more. So the extracted term, we can assume it's a multiply b plus c. It's extracted and marked in green. And the mapper searches for the sum multiply a pattern, so it fails and just use more resource than we can actually do better, where we can do the mapping inside the eGraph, so we can successfully have the DSP this design mapped in a single DSP. Okay, so our goal is to run more synthesis stages simultaneously in one eGraph, but there are some problems that makes it not that straightforward. So the first thing is there are a large spectrum of previous exact work, including Rover, Seer, eSync, and all this tool is limited into a single stage. They're working for a specific optimization goal and work only at one level, and none have been run on both optimization and mapping simultaneously, and none have been on both word and bit level. So our take on this is that there are no prior exact representations that can really bridge the word and bit level in one eGraph. And so the second problem is the direct syntactic word-bit bridge is will expose the eGraph. This is a very classic eGraph issue. If we use the Verilog slice and concat by syntax, for example, with a 3-bit signal S, we have 4 different forms of expressing it in the eGraph, and this will give us actually exponential many different forms to be rewrite and discovered. So our fix is to use the underlying semantic equality that the underlying bits of 2-bit vector is equal, means that the 2-bit vectors are equal. And the insight is very straightforward, but we can use such semantic invariant to replace the exponential many syntactic form. So there's another question: how do today's engine maintain this invariant efficiently? Actually, we can do an implementation within the E-class analysis framework. So we can make a relation of has bit for a bit vector to has its concrete bit in a vector. However, it's not efficient. Computing the bits directly is cheap, but maintaining the equality is not. At least we need 2 different direction of propagation of the equality, either a forward direction where we want to propagate the equality from the bits to the bit vector, or we want to do the backward propagation from the bit vector to the bits. And we need to do pairwise comparison between the bit vector or the class analysis facts. So this is our motivation for introducing semantic eGraphs. And so there are 3 problems, and we have 3 ideas. In order to deal with the phase ordering issue, we bring the multi-level representation, and in order to deal with the direct syntax, bridge explode issue, we introduced the semantic EID, which replaced the opaque EID and reflects the semantic value of the E-class. And in order to maintain the invariant efficiently, we have some operator like semantic constructor and decomposer to make this happen. So let's have a review from the egraph EID. Traditional egraph has the opaque EID, and it's a opaque identifier could be an integer that represents the egraphs, but not carrying its semantic meaning. And we are replacing it with a semantic identifier from a user-defined domain, and it is the E-class semantic value. And there is a concrete value for the successful interpretation case, so we can merge the equal SEID classes. And we also have the fallback case where we return a symbolic SEID, which is equivalent to the opaque EID. So we have the semantics as the first class element in the egraph. And in order to maintain the SEID, we use the egraph X3 operation add, merge, and rebuild, and add some small semantic extension to it. For add, we add a semantic constructor. For S-merge, we add a semantic decomposer. And we all know that AG implementation is lazy, so some union happen at S-merge will be delayed to the rebuild. So we are also doing similar delay for the SEID update, and we will need to propagate them in the rebuild as well. So for insert, this is the standard insert or add, and what we add is we compute the SEID via a semantic constructor. For this case, it's a concat, and if we find a semantic EID that already exists with another E-class, then we find a free equality, or we can just do the merge. So the constructor can establish the equality at insertion, and this equality is not discovered with red rule. And for S-merge, what we add is if both SEID we have for 2 E-class are like composite type, and we can have a semantic decomposer to split the merge into components merge, and this can happen recursively. So basically, we're propagating the equality downwards to its component. And we also have rebuild. So what we are doing in addition is the rebuild process can propagate the SEID in both directions, either upward to the recompute of the semantic constructor and of the affected parents, and also if some merge happens, we may trigger the downward propagation by the decomposer. And we iterate through a fixed point. So we have some property. The SAG is sound because our equality comes from either the syntactic rewrite rules or from the relation derived by our semantics. So no like fake equality are invented, and we are maintaining the list congruence of these 2 relations. So it's sound, and also rebuild terminate. And we are back into our NextMap tool. We have the tool for hardware implemented based on the semantic egraph, and we are working on a simple domain. So the bit vector SEID is the vector of its underlying wire, and we have some hardware E-class types like the wire vector and register, and we also have cell, which are like primitive operation over these types. We have both bit level and word level logic gates and adder, mux, slice concat on word, and some DSP or technology dependent resource. They will be selected at the extraction. And here is a like concat round trip example. The goal is to recover the we originally have a 4-bit wire vector, and we first do the slice and then do the concat, and we're maintaining their SEID in the process. So we can find the concat node has the same SEID as the original wire vector. So there is a automated merge happening here, and without red rules. And here is another example for cross-level synthesize of an adder. So we have a type of bit blasting rule, for example, to a 2-bit adder, we have the word level expression in the egraph, but we use the rewrite rule to make the bit level like netlist implementation in the egraph as well. So suppose we have another 3-bit adder, and it's also bit busted. We can tell that the lower 2-bit of the 3-bit adder are the same as the 2-bit adder output. So the reason this can happen is the word level slice sharing can be propagated from the bit level netlist. So the takeaway is the word level and bit level together in one egraph can expose us more possible sharing and more optimization opportunities. So here's our workflow. We have the RTL in and have the semantic egraph do the search and optimization and mapping, and we export everything into IOP constraint and do the extraction and output the map design as a final result. And all our synthesis passes share the same graph. We have technology-independent rewrite, including the arithmetic, bit busting, and some logic, and some retiming. We also have technology mapping rule for based on a user-supplied tech lib, and we have target cells like DSP, DRAM, expressed as rewrite rules. We actually have some recursive pattern for target some repetitive cell structure. And on our extraction, after the saturation, we do some encoding in IOP to extract a type-consistent implementation from our stack. And the general model is there's a binary variable pick one cell from each E-class, and we have the constraint for driver consistency, and we minimize the resource cost. And we have the legal loops checking. So basically register our model in our design. So the feedback loops are expected, and we don't allow the combinational cycle, but that's actually automatically handled. The third point is we have the timing aware constraint encoding by the critical path based on like path by the E-class and E-node. And the combinational loop will imply the unbounded delay. So because we have constraint on delay, so we will automatically eliminate the combinational cycle issue. And for the complex technology cell, we deal with some non-uniform input-output timing and internal pipeline issue with the split and bind method. And for our evaluation, we have two research questions. The first one is NextMap's quality, like how is the quality compared to the existing tools? And the second question is, does the running optimization and mapping simultaneously actually helps? So we have two more in paper. And for the first research question, we compare against Theosis and commercial tool. Compare against Theosis, we are better on every resources and overall 25 fewer DSP at scale. Compared to commercial, we are competitive, and they're sometimes better, but we are overall like at the same scale, and we have some benefits in some designs. So the running time is like overall short, and for largest 400,000 wire size design, we run for 32 minutes, and both time is in IOP. So we are competitive with a commercial tool at scale. And we have an evaluation study for NextMap against the phase order NextMap, and we have identical rule, but they are executed in separate phases with like extraction between each, and we can say that NextMap always ties or beats the phase order NextMap, and we can sometimes gain very substantial gain from it. So our conclusion is the problem is the prior EQSAT tool stop at one stage, and we propose semantic egraph to get more semantic equality efficiently from the SCID as the first class of encoding of semantics. And we implement the NextMap tool to bridge the word and bit level, do more synthesis passes at once, and get competitive result to commercial tools. And this enables optimization beyond the reach of vanilla EQSAT for EDA. And actually, beyond hardware, we believe this should generalize to any domain with like composite type or some structure, semantic value, including string set polynomial. So we can see there could be some potential there for future exploration. Okay, so that's all. Thank you.
Well, let's thank our speaker. We have time for about 2 to 3 questions.
Cool, thanks. I'm Elam from MIT. I'm just curious, just one question about your evaluation. Did you hit the same critical or the same max frequency on everything? And did all of the evaluations take the same, like wall clock or cycle count duration? Like, is it doing any like wacky, pipelining or anything that?
I'm not exactly the person doing this evaluation, so I'll suggest you check with the JIT.
Okay, thanks.
I have 2 questions, and the first is basically the same. And uses is basically not considering the performance. It does not optimizing the fine note, something like that. And maybe that's why the evaluation is not reporting the max frequency. And my next question is, the method seems quite general and may be applicable to multiple backends beyond FPGA, right? And but in experience, different backend may have vastly different performance based on, even they are optimized through identical passes. So I'm wondering if there are any subtleties behind this selection of
Okay, thanks for the question. I think for the first one, even though I'm not sure about the detail, I think the framework can support different kind of like we can weight different kind of optimization go together. We can include the fan out, the power, the area. If you have some estimation over it, we can add it into the IOP like formula. That's doable. And for the second question, yeah, I think it's very exciting that we start everything from like working on EDA with equality saturation. So and then we come with a tool and we want to like develop a series over it to like explain what's happening here. Definitely. We can try more other semantic domain that may have different implications there. And I think it's generally like very promising, but there are also some issues that different semantic domain may influence the maintenance of the SEID. So we may lose some like good property we can claim here, but it's still like I think it's very exciting to be explored.
Okay, let's thank our speaker again. So our next speaker is Gan Xiang, who is going to introduce this properly named framework called Quasar that applies equality saturation to optimize quantum circuits.
I'm Gan Xiang from Columbia University. Today, I'm going to present our work, Quasar. Can you give me a... Yes, right. Okay. Check. Okay. So today, I'm going to present our work, equality saturation for quantum circuit optimization. This is a joint work with Peggy Run and Renzhou Tao from University of Maryland and Ronghui Gu from both Columbia University and CERTIC. So our project is primarily focusing on optimizing quantum circuits, which are composed by a sequence of quantum gates operating on a set of quantum qubits. And the motivation here is that why we need to optimize a quantum circuit is that every quantum gate carry noises, which means that when we are running a quantum circuit over a real-world quantum hardware, each gate is subject to error and may produce incorrect results. So therefore, the more quantum gates that the circuits that we run for on the hardware, then the higher probability that we can get an incorrect answer. So the optimization objective for us is to minimize the number of the noisy gates over the whole circuit while preserving the functional equivalence between the original quantum circuit and the optimized ones. Therefore, we can maximize the correction rate about each quantum circuit of the quantum algorithm. That namely improves the quantum circuit fidelity. And the most advanced and the most widely used quantum circuit optimization method for now is a circuit rewrite. That is a pattern matching and a substitution to pattern match a sub-circuit inside the to-be optimized circuit and substitute with another one. And this is quite similar and with the people optimization in classical program optimization. So here is a few examples here. For example, the CNOT gate cancellation rewrite rule will cancel two adjacent CNOT gate into an empty circuit, and the rotation merge rule will merge two adjacent rotation gates into only one and accumulating their phases. And there are also some commutation rules to rewrite and reorder two adjacent NOT gates or the CNOT gates and to reorder their position in the gate sequence. So having seen the rewrite as the primary optimization results, the next question is that how optimizers apply those rewrites. And we found that this is not a trivial question, and this will later will limit the capability of optimization in the quantum circuit optimization. So we do a survey and classify most of the quantum optimizers into two categories. The first is the heuristic-based industry-level quantum compilers, including the QSKit and TKit. They manually crafted a carefully designed small set of rewrites, including tens or even hundreds of rewrites, and they apply those rewrites in an empirically designed rewrite sequence or a greedy function or a greedy algorithm. And another type is a search-based algorithm, mostly in the state of the art and in the recent years, including the Quartz, Quasar, and Quark. Instead of using heuristics, they leverage the super optimization idea based on the classical optimizations to automatically synthesize a large size of rewrites composing thousands, tens of thousands, or even millions of rewrites. And then iteratively apply those rewrites selectively. In each iteration, they will apply only one single rewrite, and this rewrite is selected from such a large rewrite rule set coupled with a specific search algorithm, such as the beam search, the simulated annealing, or the reinforcement learning. However, the question is that no matter what optimizer they are, and no matter what search algorithms that they use, no matter they are heuristics or the search-based, all of them apply those rewrites sequentially. So what is means by sequential? Sequential means that the rewrite just takes the output about the previous rewrite as its next rewrite as its own input, and to do that iteratively. So what's the problem with the sequential? So let's use an example to show how the sequential can lead to the suboptimality during the circuit optimization. So this is a real-world quantum circuit example, and this is a correct optimization path. We can see that it's composed by 4 sequential rewrites from T1 to the T4, and in each rewrite it will do a transformation. However, in the real-world optimization case, we are not that always so lucky to pick such a correct optimization path. For example, what if the optimizer can apply the rewrite T3 here? And this is not that rare because in each iteration and each rewrite rule application, we have thousands, tens of thousands, and millions of rewrites that can be picked. And if that transformation was applied instead of T2, then it will. And so in that case, we are not that lucky and we'll get stuck because after transformation, there is no possible pattern match that we can find with the current or coupled rewrite rule set. So therefore, the optimizer found that there is no pattern match found. So therefore, the whole optimization got stuck, and so no further improvement yet. So this phenomenon that the order that we apply those optimization can influence the final optimization result is not a fresh result. It's a well-studied problem called the phase ordering problem, studied by the Leverett et al. In 1979. Although this phase ordering problem has been well-studied and meditated in classical program optimization, we found that since that all the quantum optimizers previously applied those optimization in a sequential manner, so the phase ordering problem limits their capability and remains to be unsolved. Therefore, we present Quasar, equality saturation for quantum circuit optimization. First, it handles the suboptimality caused by the phase ordering problem and other root causes by using equality saturation and leverage E-graph to represent and to do the exploration. And second, it proposed a series of optimizations to both reduce the circuit rewrite redundancy during exploration and also improve the E-graph scalability on the circuits. Finally, our evaluation shows that Quasar stands for the best optimizer across all the optimization times and all the possible metrics, and over 100 circuits that our benchmark included. And this figure shows the overview about the Quasar equalization, and I suppose all of you have been quite familiar with this equalizations, and so it's just a brief talk. It's just a brief representation that each input circuit are represented into the E-graph, and we do the rewrite to explore all the E-graph and finally do the extraction. So here, first it will do an initialization to the E-graph, and for simplicity here we just represent the quantum circuit as the sequences and encode them into the E-graph. And for the paper, it have multiple encoding approaches. So it will first encode the input circuit 1 into the E-graph, and to explore in the exploration, it will do multiple rewrites. For example, here, circuit 2 rewrite will do a C0 gate and NOT gate commutation and store such a intermediate optimization result into the exploration and put them into the same classes with the original one. And then it will do a NOT gate cancellation that is matched with the circuit 2 variant stored in the E-graph. And this variant, circuit 3, will also be stored into the E-graph. Finally, it will do extraction under the user-specified cost model. And in this case, the best circuit is obvious, is definitely the circuit 3, because it has the least number of the noisy gates. That is, it only includes a C0 gate. And so it drops the circuit 1 and circuit 2. And given that extraction result of the E classes and E nodes, it will reconstruct the final output circuit. However, there are a few challenges for equality saturation to apply to the quantum circuit. It's driven us to develop a series of optimization, both offline and online. So due to the time limit, I will only discuss about the offline optimization and leave the online optimization works for the scalability issues to the paper. So the offline, major challenge is that we found that there are so many rewrites that we can apply during the equality saturation, and this prevents us from achieving valid optimization results before running out of resources. We can see that many previous work has exploited powerful rewrites, including the Quartz, Quarrel, Quasar, and Gork. They include tens of thousands of rewrites, and if we just apply them naively to directly apply all of them to the E-graph, and after 10 iterations, it will run out of memory and about 100 gigabytes of memory, and cannot generate any valid results in about 2 hours in most of the circuits. So the bottleneck is about the E-matching, right? We are applying so many distinct rewrites simultaneously to the E-graph. This pattern matching will indeed cost a lot. So our insight here is that although these rewrites are exploited by those sequential optimizers, they are powerful, they are useful, but they are not that necessary to include all of them in the equality saturation scenario. They are composable and redundant in the E-graph case. And even better, we can find atomic rewrites that are small enough, that are orthogonal and non-redundant, and at the same time preserve the optimization capability as strong as the original large rewrite set. For example, this is a 3-qubit and 5 quantum gates rewrite, and we can find it reduced quantum gate from 5 to 2, and actually it can be decomposed into 3 distinct and smaller atomic rewrites that are composable, include a smaller number of the gates and the qubits. So how can we find that one? So a rewrite is composable and redundant under a rewrite set R, as we previously discussed, can be, as long as it can be composed by a sequence of combination of sequential rewrites from the left-hand side term to the right-hand side term. And we found that finding such atomic rewrites can also be done by leveraging equality saturation. Given a left-hand side term, we can apply a currently we found atomic rewrite to saturate such a left-hand side term. And if the right-hand side term is also be found in the E class, then that means we can find a equivalence combination of the rewrite trace from the left-hand side to the right-hand side. Therefore, this rewrite can be safely reduced without any degrade about the optimization capability. And if that's not found, this atomic rewrite can be added to the current atomic rewrite set. By leveraging this technique, we have squeezed the rewrites over tens of thousands into just exactly 40, and this is a pre-processing offline optimization to achieve that. So as previously discussed, we only talk about only one optimization, and we will jump to the evaluation. We learn about 40 atomic rewrites, and we evaluate our Quasar optimization results over 176 algorithms with over the IBM Eagle gated set with the newest quantum parameters. Our evaluation shows that Quasar is the best optimizer across all the optimization times, which means that, as shown in the figure, that with the x-axis to be the optimization time, we allow each optimizer to run from 1 minute to over 2 hours. And the y-axis represents the gate reduction rate as a metric for evaluating the optimization quality. The higher the better. We found that, as shown in the orange line, the Quasar can dominate all the, can find the best results across all the benchmarks after we left him run up to 1 minute, and it will dominate all the optimization results. Furthermore, we found that Quasar is not only the best optimizer on all the times, but also on all the metrics. We evaluate Quasar on 4 metrics that all the previous optimizers evaluated, including CNOT gate reduction rate, total gate reduction rate, fidelity, and circuit depth. And most importantly, it can beat QSKIT in over 100% in the CNOT gate reduction rate. And in general, it can mostly find a better solution over 80% of the circuits than all the others. And we also show that compared to the other rewrite rule sets, the atomic rewrite rule set is the best set that can be the fastest and can have the best optimization quality. Okay, so time to summarize. We present Quasar equality saturation for quantum circuit optimization. It foresolves the sequential optimizer suboptimality challenge caused by the phase order problem by introducing equality saturation on the graphs over the circuit. And it also reduced the rewrite rule redundancy during the exploration by introducing an offline atomic rewrite rule inference, also by equality saturation. And also, in our paper, we also discussed the scalability of equality saturation over the quantum circuit by introducing two solutions. So one is the equality saturation-based solution called scheduled equality saturation, and another is a quantum-driven solution called ILP-based reordering to use integer linear programming to reorder the gate sequences, thereby reduce the efforts in the exploration. And in total, it is the best optimizer for now across all the metrics and all the benchmarks. Thank you. Quasar is open source, and please scan the code to try it out. And I'm happy to take any questions. Thank you.
Okay, we have time for 3 questions.
Hi, thanks for the good talk. So most equality saturation domains don't have so many rewrites, and in your case, you minimize it to a smaller set. But why are there so many rewrites, at least to start with, in this domain?
Oh, you mean the initial rewrite set about
the one that was.
Yeah, we will. This is because the rewrites are the term of the equation comparing of the left-hand side term, left-hand circuit and right-hand circuit, right? And this equation can be generated by by enumerating the possible combination about the atomic gates, and the initial equivalent checking can be done by linear algebra checking, because each quantum circuit can be represented as a linear algebra matrix. So, and therefore, and since that each red set is not that big, it only includes several qubits, and each terms include several less than 10 quantum gates. So that comparison over the matrix is not that big. Its cost is low. Okay, thank you.
Hi, thanks for the talk. So my understanding is that in quantum, there are often rewrites that can be applied with some probability. And in this case, as far as I understand, like all the rewrites are
unconditional.
Unconditional. So I'm kind of curious if you think that E-graphs can be used to apply these probabilistic rules.
These probabilistic-based rewrite rules and are also including the resynthesis-based quantum optimizers that I do not discuss in this paper. And these are considered as orthogonal work to apply those probabilistic-based rewriting and the quantum resynthesis and integrated into the Quasar. Yeah, and we are expected this to be a future extension to our Quasar work. Thank you.
Great talk. There's a well-known complete equational theory by André Clement and co-authors for quantum circuits, and I believe that that's under 50 equations, probably on the order of 25, though you can correct me if I'm wrong. Did you try plugging in that set of equations into the eGraph tool, and was this better?
Sorry, excuse me. Which rewrite rule set?
There's a few papers, but there's a paper by André Clement and Simon Perdis and others that is a complete equational theory for quantum circuits. So that should get you from any quantum circuit to an equivalent one. And I believe it's under 40 rewrite rules, so I haven't counted them. So I was just wondering if you tried plugging in any of the results from those papers into the eGraph tool and wanted to see whether or not you could get the results.
I think we can do such an evaluation to evaluate the quality about the Clemens et al.'s rewrite rule set comparing to our atomic rewrite rule sets in future. Thank you.
Okay.
Okay, let's thank Ganxiang again. So for our last talk of this section, Zachary Sisco will tell us about fungible memories. So as a normal person, I'd like to think my memories as non-fungible because you only live once. However, it turns out that this is not the case in computer hardware. So this talk will introduce the abstraction of fungible memory that pushes the state of the art on hardware compilation and retargeting for memories. Okay.
All right, hear me? Great, thank you for the introduction. Okay, yeah, so like the introduction said, in this work we're focusing on a particular hardware design problem. And so yeah, we're proposing this language abstraction called fungible memories, which gives us a write once, map anywhere memory abstraction that hardware developers can use to target many different memory technologies from a single generic interface. Okay. In this work, we incorporate fungible memories into a memory compiler, which automatically targets many memories according to the different technology constraints. And then we also go in the other direction. We also build a memory decompiler, which lifts memories from existing gate level or simulation-ready designs up to fungible memories to enable technology retargeting. Okay? And so to accomplish this at scale, we developed a structure-aware equality saturation technique, which scales to net lists with millions of cells and identifies memories that state-of-the-art tools cannot. And so while we're in the equality saturation session, this work really touches on a very specific hardware design problem. And so I want to kind of set the stage a little bit, give an example, right? So how do hardware developers design memories, right? Let's consider a register file, right? So here we have a nice little block diagram of our register file, has 3 source inputs, a destination register to write to. If we're using a hardware description language like Verilog, we would normally describe it like this in a behavioral way, right? We can model our register file as a two-dimensional array of registers. We can use familiar array notation to read to it, to write to it, and that's great, right? This works fine for simulation, But if you want to deploy this to something like an FPGA or any real piece of hardware, this kind of implementation does not always work, okay? And the reason is that languages like Verilog do not provide technology-specific constructs in the language, right? A device like an FPGA has things like BRAMs to describe memories. And Verilog doesn't really know what a BRAM is, right? Now, there are some mitigations to this, which I'll talk about in the evaluation, which we compare to. So in this case, what does a developer do if they want to deploy this on an FPGA or an ASIC or anything like that? Well, they need to write a custom mapping for this register file to be able to map it to BRAMs on a particular FPGA, right? So in a language like Verilog, what we see a lot are these if-def blocks. So developers will split parts of their code for each memory into a separate if-def for each technology target that they want to work for, right? And so our developer here will make a new if-def block for their FPGA target. And so what did they put in here? Well, for that particular FPGA, they'll read up into their, they'll pull up their vendor manual that describes how to instantiate that BRAM, and they'll figure out how to do it. This is one example of a particular mapping. It has all these different parameters and ports that they have to hook up in the right way, right? And it's not always that easy because this mapping can be a little tricky, right? It's not always the case that we have a one-to-one mapping between our behavioral memory design and the one that would conform to a particular technology, right? And so in this example, the interface for our register file has 3 read ports and 1 write port. A typical FPGA may only support dual port BRAMs. And so the developer actually has to make a custom mapping which will kind of map their 3 read port, 1 write port memory into a configuration of multiple dual port BRAMs, which emulates the behavior of a 3 read, 1 write memory, okay? And so these are transformations that the developer has to make, okay? And this is just the register file. This is a little data path diagram of a CPU. If we're developing a CPU, we have many more memories in our designs. This mapping process has to be repeated for each of these different types of memories, and they have their own configurations and semantics as well, right? So this makes refactoring a pain on the code base, right? If we want to support new technologies, we need more if-def blocks if we're using this kind of technique. If we change the behavior during the development process, the design process, we need to refactor those blocks in a consistent way, right? And so the takeaway here is that technology constraints make this implementation brittle to design changes, right? And the language that we're using, Verilog, isn't really providing us any helpful abstractions. And so that's where fungible memories come in. So a fungible memory enhances our hardware description language because we try to capture the shape of connections and portedness of memory blocks in hardware designs, okay? So in this paper, we formalize an algebra of fungible memories where ports and memory blocks are objects that can be constructed and rewritten according to a set of semantics preserving rewrites, okay? This is a list of just kind of the different rules that we include in the paper. This involves splitting memories by read ports, write ports. We can also merge them together. We also do rewrites according to the shapes of our memories. You could split by width and height and so on. We can also do casting between port configurations as well. So this is an example of a read port splitting and merging rewrite, right? We could start with a memory that has k read ports, and we could split one of those read ports out into a whole separate memory block in this way. So the visualization is on the top, and how we actually formalize it as a memory is on the bottom, okay? We can also support other kinds of kind of function splitting and merging as well. Certain memories might support optimizations like write-to-read forwarding, where you would forward the value of a write to a read port, right? Some memory blocks would support this as a flag, and some don't. And so depending on your technology constraints, you would either want to kind of fold that logic into the memory if it's supported, or if it's not, you want to break it out into separate logic so that you could still map the design, right? And so in the paper, we describe a handful of other rewrites over a fungible memory algebra, and then they have various, we have a formalization of that. And the last thing I'll mention about this is because this fungible memory algebra is kind of introducing a sort of new equational theory of memory blocks and hardware, we wanted to have some confidence in it. And so we formalized fungible memories in Lean because we wanted to prove that the rewrite rules that we constructed actually preserve behavioral equivalence according to memory read-write semantics. So that's described a little more in detail in the paper. The Lean source code is also in our artifact as well. Okay, so with fungible memories in hand, we incorporate that into an existing hardware description language so that we can do this automated memory technology mapping, right? The problem kind of roughly looks like this for our memory compiler, where we have a set of fungible memories, we have some technology constraints, and we want to try to figure out, using our rewrites, how can we reshape our memories to fit the technology constraints? And that gives us a satisfying mapping, right? So as one concrete implementation of this, we extended Perl, which is a Python-embedded hardware description language, to support fungible memories. As one particular case study, we ported a 5-stage RISC-V CPU to use fungible memories. One benefit of this is that we were able to kind of shrink our memory implementation in Perl from 130 lines of code to 3, one for each memory block in the design. So a very kind of declarative memory specification now. And this also comes with the benefit of getting a bunch of different technology backends for free. So that's something that Perl really just focuses on simulation, but now with this automated technology mapper, we can then target many different memory backends. Okay, so that's the memory compiler direction. The other direction for this is the memory decompiler, right? And so this is important for this memory retargeting scenario, right? And so there's a lot of different kind of more and more open hardware designs out there. It's common more and more for developers to compose their designs kind of with different components, put them together. And some of those may have been developed with a different technology in mind, or maybe developed with maybe just technology abstract, right? So what if we wanted to integrate those components into a new design and retarget it to a new technology? That's where memory decompilation comes in. We want to identify these memories in our design and lift it up to fungible memories, okay? So the way that we do that, I'll kind of give a really brief overview of how this works. So this would, in kind of the most basic case, you would start with a gate level netlist, and you would analyze that gate level netlist. You have all the different flip-flops and logic and try to identify memory blocks in there, right? So the first step would be grouping flip-flops into wider registers based on common enable signals, and then kind of building out different memory block candidates. We have a set of rewrite rules for identifying read port logic, which often works over like a mux tree reduction. We have kind of a symmetric set of rewrites for identifying write port logic, which kind of works over demux reduction. And then putting all those things together, we then identify all those common pieces and extract all the different fungible memories in that design. And so the key technique to doing this is equality saturation. And it's really kind of a perfect setup for equality saturation because we have this huge kind of blasted out gate level netlist, thousands, even millions of low level logic cells. And with a lot of the aggressive logic optimizations that hardware synthesis tools may perform, it's really not obvious what sequence of rewrites will reveal this kind of higher level structure that we're looking for, right? Now, for anyone who's used equality saturation, like rewriting over an egraph with millions of nodes is not going to be a fun time. And so in order to actually implement this and get it to work, we had 3 key optimizations to help with this. The first one we call structure-aware scoped rewriting, right? And so a lot of these logical rewrites that we might perform over a gate-level netlist can apply almost anywhere in the netlist, right? And that's going to increase rewriting time and grow the egraph unnecessarily. But since our goal is memory decompilation, we really only care about signals whose source or sink is a register. And so we do this sort of like structure-aware rewriting to really cut down on where we're applying some of these rewrites, particularly mux tree reduction. We really only care if that's connecting to register sources. So that's a really key one. Another very useful one is subsumption. During register grouping in the initial phase, we only really need to choose a single representation of grouped registers rather than maintaining every possible grouping of flip-flops. So we will subsume all other groupings. That's also a big saver. And then another really helpful one are inverse transformations. And so this comes from the Selinsky work. And this is about inserting speculative equalities into the E-graphs and later validating them. And so we adapted this to netlists because using inverse transformations is really useful when we're rewriting over netlists because hardware synthesis tools might apply these really aggressive optimizations, which we need to undo to kind of reveal some latent structure that was hidden by those optimizations. So that's a very helpful technique there as well. Got it. And then the last one, and this is probably the most twisted one, is that we implemented our equality saturation engine in SQLite, okay? And, and so we know from egglog and other recent research that there's this beautiful connection to relational databases and equality saturation. And we took this to the extreme, and to good effect, I would argue, right? And so kind of doing things directly in SQL, we could really easily implement a lot of these optimizations without maybe some of the guardrails that equality saturation frameworks might impose. And certain phases, like grouping registers by common signals, we can do those kinds of queries very fast in relational databases, right? And so this kind of helped us break some rules for doing decompilation, which I would argue, since we're decompiling anyways, it's okay to be a little messy. And so we could sometimes skip some expensive steps, which normally come up, okay? And so putting all of this together, we have this tool called Memo, which comprises the compiler and decompiler for fungible memories. It looks like this. The user would either input a design expressed in Perl extended with fungible memories, which would then go through the automated memory technology mapper alongside different technology constraints. We have a number of backends spanning simulation platforms and ASIC and FPGA memory technologies. And then alternatively, a user can input an existing design as a netlist, go through the memory decompilation step, use those fungible memories to then retarget to a new technology. I'll briefly go over a bit of our evaluation here. We have more details in the paper. But a big aspect of evaluating this is actually with the memory decompiler, because this is enabling us to compare over existing designs and compare with related techniques, right? And so in this table, we have a handful of open source hardware components that include things like caches, FIFOs, a couple of small RISC-V cores, and other SoC components, right? And so in each of these designs, there is an expected memory. And sure enough, we were able to decompile and identify those memories and their kind of original configurations. Decompilation time is fast for these. And what we wanted to do is we wanted to compare it with something that was the most similar kind of operation to what we're doing. And that would be memory inference in hardware synthesis tools. And so hardware synthesis tools like Yosis and other FPGA synthesis tools have a thing called memory inference, which is more of a syntactic pattern matching operation, where it looks at the Verilog code, kind of matches over a syntactic template. And if you don't perfectly match that, then it's not going to identify the memory. And so memory decompilation works over the structure of the netlist rather than just a syntactic template. And so we're able to identify memories over designs that Yosis missed and even some commercial tools missed. We have a handful of large-scale case studies from some open source hardware designs where we do memory decompilation and then also do retargeting to different FPGA and ASIC technologies. One example is the Spark core has the netlist that we decompiled had more than 700,000 gates. Memory decompilation took about a minute, and we recovered all of the expected memory blocks. A bigger one, we decompiled an L2 cache. That was 1.5 million gates. It took about 2 minutes. And indeed, we correctly identified all the expected parts of the cache, tag, state, data blocks, and all of that. And then our biggest case study was the open source Black Parrot RISC-V multi-core SoC. The kind of synthesized code for this is about 12 million gates. Memory decompilation took about 6 minutes. And we went through and checked, and we identified all of the expected memory blocks in that core, in the front end and the back end, okay? And so to wrap things up, kind of a more broader level takeaway, I think in hardware description language design, technology specialization is perhaps a bit overlooked. I think there are indeed some useful abstractions that we can kind of pull out to improve the development process in this way. I think fungible memories are one instance of this observation, right? So we developed this kind of equational theory of how we can think about memory design, and then using powerful rewriting techniques like equality saturation, we can improve different aspects of synthesis like tech mapping. And we can do it at the scale of real-world SoC designs. And so my question is, what other equational theories are hiding in the hardware development process that we can kind of think about and build into our tools? So, like I said, our tool memo is open source. That is the compiler and the memory decompiler and its its lean formalization. I would encourage you to check it out. And yeah, thank you all very much.
Well, thank that. We have time for 2 questions.
Sometimes the synthesizer may using some correlation analysis to identify that some parts of the memory is dead and it could be eliminated. In that case, the signature of the memory is changed. Is that a problem in your tool, or we are stay faithful to the user's specifications?
Sure, yeah, this actually comes up really importantly in our write port decompilation stage. So when we're looking at things like register files in CPU designs, a lot of times we would find that the synthesis tool would kind of erase the demux, like the parts of the demux tree related to the 0 register, right? Things like this. And so that's where techniques like inverse transformations really help us, because they help us undo some of those aggressive optimizations that synthesis might do. Yeah, so that is one example of that.
Okay.
Thanks for the talk. It's a bit sad to see that people would rather use SQLite than Egglog. But I'm curious about your experience, like building an eGraph engine on top of SQLite. Like, what's good and what's bad about that?
Let me first say I love Egglog. I think it is a wonderful tool, and we did a lot of prototyping with it. I think the experience of writing an equality saturation engine in SQL, I think is arguably worse than writing one in Egglog, because it's like you're writing SQL queries and things like that. So it's not as ergonomic as a language that was designed for doing what it was like what Egglog does. But I think that the trade-off is we had so much more direct control over the schema, like over what we were doing. We were able to kind of be a little more messy. I would be interested in seeing, is there a front end to this to kind of describe what we were trying to do and then compile that to SQL instead of having to, I mean, you can check out our open source tools and see what the SQL looks like, and it's kind of gnarly, but it makes sense when you look at it a little closer, but it's not that fun. Not as fun as Egglog.
Okay, let's thank Zach again.
Thank you.
So just as an extra plug, Zach is also looking for prospective students and postdocs. So if you are interested in quality saturation, computer architecture, or program language in general, please talk to Zach. And this concludes our equality saturation session.